Your body runs out of energy faster than you expect, even when you are not doing much. You can sit still, eat well, sleep enough, and yet feel drained, while many animals can roam, hunt, or migrate for hours with far less rest. Something here does not quite fit the story we like to tell about ourselves as the most capable species. If survival once depended on endurance and efficient use of energy, then why does the modern human body seem to burn through energy so quickly compared to so many other animals? And what did we lose along the way that made this possible? Why does human energy run out so quickly compared to animals? Human energy feels like a private account that drains without warning, yet in nature energy is not private at all. It is a constant exchange between bodies, landscapes, and time. When we ask why human energy runs out so quickly compared to animals, we begin with a quiet idea that every living body is an engine that must pay for each movement, each thought, and each repair. The feeling of running out of energy is not only about exhaustion at the end of a long day, it is a signal that the balance between intake, storage, and expenditure has tilted. In many animals, the pattern of living fits tightly with the available energy of their surroundings, and the rhythm of their day matches what their bodies can afford. The human body carries a different story, because the structure of our bodies and the path of our evolution created a complex energy budget that is both powerful and costly. From the beginning of our lineage, the bodies that led to modern humans carried the marks of a changing world, moving through environments that were neither easy nor stable, where finding food, escaping danger, and staying warm all demanded energy. The ancestors who walked upright had to invest energy in new ways, using muscles differently than the creatures that moved on all fours, and this shift changed how energy flowed through their days. Standing upright gave hands new freedom and changed the way we moved across land, but it also required new balances of muscle tension and new forms of endurance, each drawing on the body's limited reserves. This did not mean early humans were weak. It meant that the cost of being human had a different shape, one that carried both benefits and burdens. The early body was not only a tool for motion but also a carrier of a growing brain, and that brain drew from the same energy that could have gone to muscles. In the long sweep of time, the relationship between brain and body created a new kind of tension, where thinking, planning, and remembering became survival tools, but they required energy that could not be used for running or climbing. The environment shaped these choices, because the shifting climate and changing landscapes forced human ancestors to find new ways to survive, relying on endurance, coordination, and social cooperation rather than raw speed or sheer physical strength. These strategies allowed humans to persist, but they also created a body that spends energy in ways that are less visible than the sprint of a predator or the flight of a bird. Modern humans inherit this pattern, and the feeling of quick fatigue can be understood as part of a deeper pattern that stretches back to those early trade-offs. Today, the sense of low energy often appears in moments when nothing obvious has been done, such as sitting still, thinking, or trying to rest. And this can feel confusing when we compare ourselves to animals that seem to move endlessly without complaint. Yet animals have their own balances and their own limits, shaped by the narrow demands of their habitats. While human energy is distributed across a wide range of tasks that include social bonds, communication, learning, and adaptation, the comparison can mislead us if we assume that all bodies measure energy in the same way. The human experience of energy is not simply about movement, it is about managing a complex network of processes that include immune function, temperature regulation, growth, and thought. When we ask why our energy seems to run out so quickly, we are really asking how the human body allocates its limited resources, and how that allocation reflects a history that began long before modern life. The answer will not be a single cause but a map of choices and constraints that emerged over hundreds of thousands of years, written into the way our bodies live today. The question of why human energy seems to run out so quickly grows clearer when we look at how the body is built to distribute its fuel across many quiet but constant demands. Unlike a machine that only burns energy when it moves, the human body is always paying invisible costs, even when still, and these costs add up in ways that are easy to overlook. The heart keeps beating, the lungs continue to pull in air, cells repair themselves, the brain maintains electrical activity, and the body keeps temperature within a narrow range. These ongoing processes do not pause when we sit down or try to rest, and each one draws on the same shared supply of energy. Many animals experience similar demands, yet their bodies have often evolved around more predictable environmental rhythms, allowing them to conserve energy in ways that match their ecological niche. Humans, by contrast, evolved under conditions that demanded flexibility and adaptation. And this flexibility comes with a metabolic cost that never fully turns off. Our ancestors did not live in a world of constant comfort, but they did live in a world where their energy use was closely tied to the land and to survival tasks such as foraging, traveling, and cooperating in groups. Over long periods, natural selection shaped human physiology to support endurance, problem-solving, and social interaction, but this combination meant that energy had to be distributed across many functions at once. The human brain is particularly significant in this balance, as it remains active even in moments of rest, using energy to maintain awareness, memory, and the ability to respond to unexpected events. This persistent activity may explain why mental fatigue can feel as real as physical exhaustion, because both draw from the same finite energy stores. When comparing humans to other animals, it becomes important to recognize that energy efficiency is not a single trait, but a trade-off shaped by survival strategies. Many animals conserve energy through specialized behaviors, such as long periods of stillness, metabolic slowdown, or highly efficient locomotion adapted to their environment. Humans, however, rely less on extreme specialization and more on broad adaptability, which requires systems that can respond to diverse challenges, from changes in climate to shifts in social structure. This adaptability can appear inefficient when judged by short-term energy output, yet it has supported long-term survival across a wide range of environments. From the perspective of evolutionary history, this trade-off meant that humans were not optimized for maximum energy conservation in any single setting, but rather for the ability to persist across many. As human societies developed, new layers of energy demand emerged, not only from physical survival but from the mental and social complexity of group living. Communication, planning, learning, and emotional regulation all draw from the same biological resources, adding to the sense of fatigue that can arise even without physical exertion. This complexity helps explain why the feeling of being drained does not always correspond to visible activity. Energy expenditure in humans is not limited to muscle movement, but includes the constant management of internal stability and social awareness. In early human environments, these traits supported cooperation and problem-solving, which improved chances of survival. But they also meant that energy was being used in ways that are not always obvious to conscious experience. The mismatch between how energy is spent and how it feels may contribute to the perception that human energy disappears quickly. While some animals appear to maintain steady energy over long periods, their strategies often involve trade-offs such as reduced cognitive flexibility or narrow ecological roles. Humans, shaped by a long history of environmental change and social complexity, carry a body that must constantly balance many competing demands. Understanding this balance helps frame the question of human fatigue not as a simple weakness, but as a reflection of a deeply layered evolutionary path that continues to influence daily life today. The idea that human energy drains faster than expected becomes more tangible when we examine the invisible costs that shape every moment of human existence. The human body is never fully idle, and even in stillness, a quiet storm of activity continues within. Cells rebuild themselves, tissues repair small injuries, the immune system scans for threats, and the nervous system keeps monitoring the environment for danger. These activities are not optional, they are essential for survival, yet they consume energy steadily and without pause. When comparing humans to animals, it is tempting to focus on visible actions such as running, hunting, or migration, but the deeper comparison lies in how energy is distributed across many systems that must remain active at all times. Early human ancestors survived in environments where danger and opportunity were closely intertwined, and the body had to remain prepared for sudden change. The ability to adapt quickly to new conditions came at a price, requiring constant background activity that used energy even when no visible effort was being made. In contrast, many animals have bodies that are highly specialized for particular conditions, allowing them to reduce energy use during periods of inactivity. Some species lower their metabolic rate when food is scarce or when environmental conditions allow, conserving energy in ways that the human body cannot easily replicate. Humans developed a different strategy, favoring flexibility and responsiveness over strict energy conservation. This meant that the body maintained readiness rather than entering deep energy-saving states as often or as effectively as some other species. The environment in which early humans evolved played a major role in shaping this pattern. Fluctuating climates, unpredictable food sources, and the need for social coordination required a nervous system that could remain alert and adaptable. This readiness increased the chances of survival, but also meant that energy was continually being spent on vigilance, coordination, and internal regulation. The brain in particular remained active across many states of rest, consuming energy to maintain awareness, memory, and planning. While this provided advantages in navigating complex social and physical environments, it also contributed to the sense that energy is consumed, even when the body appears still. Over time, these traits became deeply embedded in human biology, creating a system where rest does not necessarily equate to low energy use. In modern life, this inherited pattern can feel puzzling, especially when daily demands differ greatly from those faced by early humans. The body still operates under principles shaped by environments where survival depended on constant readiness. Yet modern settings often provide safety and stability that do not require such sustained alertness. This mismatch can amplify the feeling of fatigue, as energy continues to be used in ways that may not align with present-day needs. Animals that appear to maintain steady energy over long periods often benefit from more predictable ecological roles and behaviors that allow for efficient energy use. Humans, by contrast, live with a broader range of demands that include physical, cognitive, and social functions, all of which draw from the same finite energy supply. The perception that human energy runs out quickly is therefore not merely a reflection of weakness or inefficiency, but rather the result of a complex evolutionary path that favored adaptability over minimal energy expenditure. By understanding that energy in the human body is constantly allocated to multiple essential functions, it becomes clearer why fatigue can arise even without obvious exertion. This perspective helps shift the question away from simple comparisons of strength or endurance and toward a deeper understanding of how human energy is shaped by history, biology, and the demands of survival across changing environments, linking the present experience of tiredness to the long arc of human evolution and the compromises embedded within our species, while reminding us that what feels like personal exhaustion is often part of a much older biological pattern. If human energy seems to fade faster than animal energy, one reason may be that many animals are built not only to spend energy well, but to refuse unnecessary spending with remarkable discipline. In the natural world, survival is often less about constant effort than about matching effort to the exact moment when effort matters. A grazing animal may stand for long periods, but its body is not wasting that stillness. A hunting animal may sleep or rest for much of the day, then release a short, intense burst only when the chance of success is high enough to justify the cost. Birds may travel vast distances, yet their bodies are shaped for a narrow kind of movement repeated with extraordinary efficiency. Even small creatures that seem restless are often following rhythms that have been refined by selection over long stretches of time, so that motion, feeding, waiting, and sheltering all fit closely together. Human life followed rhythms too in the deep past, but the human path placed increasing value on flexibility rather than narrow efficiency. Early humans did not live as one kind of specialist. They moved through changing climates, changing food supplies, and changing social demands. They needed to walk, carry, watch, remember, cooperate, and improvise. That meant the human body was not shaped to conserve energy in one stable pattern as neatly as many animals were. It was shaped to stay available for many different tasks, and availability itself has a cost. From the beginning of our lineage, the land did not always offer predictable rewards. A foraging day might involve long stretches of searching, slow movement across uneven ground, careful observation, and social coordination before any food was gained at all. Compared with an animal whose body is tuned to one food source, one habitat, or one style of movement, the human body was paying for uncertainty. This helps explain why many animals seem calmer in their energy use. Their apparent stamina is often not endless power, but strict economy. They pause when pausing helps, lower activity when activity is wasteful, and follow internal cycles that narrow the gap between need and action. Humans can do some of this, but less completely because our species invested in a wider range of responses. The brain kept more options open, the social world required attention even in rest, and group life meant that energy was often spent not only on the self but on signals, bonds, and shared timing. In this sense, animals often conserve what humans spend. They spend less on anticipation, less on abstract thought, and often less on the social complexity that became central to human survival. This does not make them simpler in every way, nor does it make humans flawed. It only shows that the costs of being human are distributed differently. The animal body often appears efficient because it is tightly fitted to its ecological role. The human body appears quickly drained because it is carrying a broader assignment. It must remain ready for physical movement, but also for memory, language, emotional judgment, tool use, and cooperation. These are ancient burdens, not only modern ones. Even before cities, screens, and clocks, human beings were already spending energy on a wider field of demands than many other animals. What modern life does is not create that pattern from nothing, but intensify its visibility. When a person feels tired after hours that seem physically easy, the contrast with animal life can feel strange. Yet the comparison becomes clearer when we remember that many animals conserve by narrowing their lives, while humans survive by widening theirs. The farther back we look toward the beginning of human life, the more we see that quick exhaustion is tied not only to weakness, but to a body asked to do many things at once, in many environments, across many kinds of uncertainty, and that difference begins to answer why our energy seems to vanish so quickly beside the quieter discipline of animal energy. What looks like animal endurance is often a form of restraint so complete that humans rarely notice it. Many animals do not live by pushing themselves through the day in a steady stream of effort. They live by narrowing action to the moments when action is worth the cost. A large cat may seem powerful because of what it can do in a few seconds, but most of its strength is protected by long intervals of stillness. A reptile may appear patient, almost beyond measure, yet that patience is part of its energy design. Even herd animals that move across wide landscapes often do so in patterns shaped by food density, temperature, water access, and safety, not by any idea of constant productivity. Their bodies and behaviors are closely tied to conditions that repeat often enough for evolution to refine a fairly stable response. Humans came from a different path. Early human life also involved waiting, watching, and moving with care, but it placed unusual weight on judgment. A person could not simply rely on one set of fixed responses to one narrow environment. Human groups entered mixed landscapes, shifting climates, and uncertain food webs. They had to notice subtle changes, remember locations, read the intentions of others, and coordinate action across time. This meant that energy was often spent before any visible effort began. It was spent in anticipation, in social awareness, and in the maintenance of attention. That difference matters. An animal may conserve by doing less until the right moment arrives. A human often conserves less because the mind remains partly engaged even in apparent stillness. The cost is not always in the legs or arms. It is in the background work of interpretation. From the early stages of human evolution, this broad readiness was useful. It helped small groups survive in environments that could not be mastered by speed, claws, or sheer muscular force alone. Yet usefulness does not mean cheapness. The more a body depends on flexible responses, the harder it is to shut those responses down completely. This helps explain why the human body can feel tired in circumstances that do not seem demanding from the outside. A person may sit quietly and still feel spent because the system is not resting in the same narrow way many animals do. It continues to regulate posture, temperature, memory, planning, and emotional tone. It continues to monitor the surrounding world, even when danger is low. Animals also monitor, of course, but many do so through systems more tightly fitted to their specific mode of life. Human beings inherited a wider field of concern. The comparison becomes even sharper when we think about specialization. Many animals are efficient because they are built for a restricted set of tasks. Their movements, digestion, sleep patterns, and activity windows often fit together with remarkable economy. Humans are less specialized in that sense. The human body can walk long distances, use tools, adapt diet, survive in varied climates, and function inside dense social worlds. This versatility helped our ancestors spread across regions that demanded different forms of survival. But versatility usually costs more than specialization. A generalist body must keep more possibilities open. It carries extra burdens of coordination, learning, and adjustment. In deep time, this may have been worth the price. In daily experience, it can feel like quick exhaustion. So, when animals seem to preserve energy better than humans, the difference is not simply that nature favored them more kindly. It is that many species solved survival by becoming narrower, while humans solved survival by becoming broader. That breadth is one of our great strengths, but it also means our energy is often divided before the day has fully begun, and that division reaches back toward the earliest human environments, where survival depended not on being the most efficient at one thing, but on staying responsive to many things at once. The difference between how humans and animals manage energy becomes even clearer when we consider how survival strategies shape daily patterns of use and conservation. Many animals survive by aligning their behavior with predictable cycles in the environment, such as daylight, temperature shifts, seasonal food availability, and the presence or absence of predators. Their bodies and behaviors often match these cycles closely, allowing long stretches of minimal expenditure punctuated by short bursts of activity when needed. A predator might rest for most of the day, rising only when the odds of a successful hunt justify the energy spent. A prey animal may move slowly and steadily, avoiding unnecessary bursts of speed that would waste energy unless escape is required. In contrast, human survival strategies emerged in contexts where the timing of action could not always be predicted by simple environmental cues. Early human groups faced shifting climates, irregular food sources, and complex social dynamics, which required readiness not only for physical tasks, but also for coordination, communication, and learning. This need for constant readiness meant that even when not engaged in physical labor, the human body was often preparing for future challenges, maintaining awareness, and managing internal processes that supported social and cognitive functions. These background activities consumed energy continuously, reducing the capacity for long periods of true energy conservation. Over time, this pattern became deeply embedded in human biology, creating a baseline level of energy use that is higher than in many animals whose behaviors are more tightly bound to environmental rhythms. The consequences of this pattern can be seen in the way humans experience fatigue, which often arises not only from physical exertion but also from sustained mental effort, emotional regulation, and social engagement. Unlike many animals that can enter states of reduced activity or metabolic slowdown during periods of low demand, humans maintain a relatively stable level of physiological activity even when external demands are low. This stability supports the complex behaviors that define human life, but also contributes to the perception that energy runs out more quickly. The trade-off becomes more apparent when comparing humans to animals that have evolved specialized strategies for energy conservation. Many species rely on instinctive patterns that limit unnecessary movement and reduce energy expenditure during times when food or safety is uncertain. These strategies allow animals to stretch limited resources over longer periods, maintaining energy reserves for critical moments. Humans, however, evolved to prioritize flexibility, enabling survival across a wide range of environments and circumstances. This flexibility requires systems that remain active and responsive, drawing energy even in the absence of immediate action. The human nervous system, for example, remains engaged in processing information, anticipating outcomes, and managing social interactions, all of which contribute to ongoing energy expenditure. While this investment supports complex problem-solving and cooperation, it also means that energy is continually being used in ways that are not always visible. In early human environments, these traits provided significant advantages, allowing groups to adapt to changing conditions and exploit diverse resources. Yet the same traits also meant that energy was rarely conserved in the same way as in more specialized animals. As a result, the human experience of energy is shaped by a tension between the benefits of adaptability and the costs of maintaining constant readiness. This tension persists today, influencing how quickly energy feels depleted even in contexts that do not appear physically demanding. When we observe animals conserving energy with apparent ease, it is important to recognize that their strategies reflect different evolutionary solutions to survival. Humans followed a path that favored broad capability over narrow efficiency, and this path continues to influence how energy is used and experienced. The sense that human energy runs out quickly is therefore not simply a matter of modern lifestyle, but a reflection of deeper evolutionary patterns that shaped how our species survives and functions in a complex and changing world. The human body may seem physically modest beside many animals, but one of its greatest energy costs is not found in the limbs at all. It is found in the head. The human brain is not large in proportion to the whole body when compared with every animal on Earth, but it is unusually expensive tissue, and its expense helps explain why human energy can feel fragile even when the body has not moved very far. A creature that survives mainly through fixed routines, narrow instincts, or highly specialized behaviors may spend more energy in moments of direct action, yet less in the ongoing work of interpretation. Humans followed another path. Over a long evolutionary span, our ancestors became increasingly dependent on attention, memory, prediction, and social understanding. These abilities did not appear all at once, and they did not make early humans all-powerful, but they slowly changed the balance of the body. Energy that might otherwise support more muscle, more passive endurance, or deeper forms of metabolic slowing had to be shared with a nervous system that remained active even during quiet moments. This matters because the brain does not wait politely for physical work to finish before asking for fuel. It is already using fuel while the body is still. It helps regulate posture, interpret sound, scan faces, maintain language, recall locations, and imagine what may happen next. In the early human world, this constant activity could make the difference between eating and going hungry, between social acceptance and exclusion, between noticing a threat and missing it. A larger investment in brain function was therefore useful, but usefulness is not the same as efficiency. The cost of a more capable brain is that the body becomes a less simple energy machine. From the beginning of human life, survival depended not only on movement through landscapes, but on movement through information. A person had to remember where water had been found before, which plants were safe in one season and less useful in another, how group members behaved under stress, and how to prepare for change before change became obvious. This meant that human energy was being spent on layers of life that are less visible than running, lifting, or fighting. Many animals also learn, remember, and solve problems, of course, but the human path placed unusual weight on these traits, and that weight had to be carried metabolically. The result is not that humans became weak, it is that our strength shifted into a more expensive balance. We gained forms of flexibility that widened our ecological range, but we also became a species that pays heavily for being mentally awake. This may be why modern fatigue can feel confusing. A person may think, read, worry, decide, speak, plan, and respond to others all day, then wonder why the body feels depleted in the absence of obvious physical labor. The answer may begin far back in the past, where the human body was already becoming a partner to an increasingly costly brain. Even before agriculture, before cities, before written language, the energy budget of human life was moving in a distinctive direction. The brain was not replacing the body, but it was claiming a larger share of the same limited resources. Animals that seem tireless beside us are often operating with narrower demands, more specialized routines, or cheaper patterns of ongoing information processing. Humans, by contrast, live in a body where thought itself is part of the survival bill. That bill has ancient roots. When we ask why human energy runs out so quickly compared to animals, one honest answer is that our species built part of its survival on a metabolically costly organ that keeps working in silence, drawing energy long before the muscles announce that they are tired. The energetic cost of the human brain becomes clearer when we look at how continuously it operates compared to other parts of the body. Muscles can rest, and many organs can slow their activity during periods of calm, but the brain rarely enters a true low-energy state. Even during sleep, when the body appears inactive, the brain remains engaged in organizing memories, regulating bodily functions, and maintaining the basic processes required for survival. This ongoing demand means that a large portion of the body's energy supply is directed to neural activity, whether or not conscious thought is taking place. For early humans, this constant neural activity provided significant advantages in environments where survival depended on anticipating threats. navigating complex social relationships, and remembering patterns in the natural world. Yet it also meant that energy was continuously consumed in ways that did not always correspond to visible effort. Many animals also rely on neural activity, but the scale and persistence of human cognitive demands set a different baseline for energy use. The brain's need for a steady supply of fuel places limits on how much energy remains available for other bodily functions, including sustained physical activity. This trade-off helps explain why humans may feel drained even when physical exertion has been minimal. In ancestral environments, where resources were often uncertain and tasks varied widely, this balance between mental and physical energy could determine survival. A person might need to track subtle changes in the landscape, interpret social cues within a group, or plan complex actions that required coordination over time. These activities demanded sustained attention and memory, drawing energy from the same pool that supported movement and physical endurance. Unlike some animals that can enter states of reduced metabolic activity during periods of scarcity, humans maintain relatively stable brain activity across a range of conditions. This stability supports flexibility and adaptability, but reduces the potential for deep energy conservation. Over time, the evolutionary emphasis on cognitive flexibility shaped a body in which energy is continually allocated to mental processes, even in moments that feel restful. The consequences of this arrangement are not always visible, because the work of the brain often occurs without conscious awareness. Background processes such as monitoring the environment, regulating emotions, and maintaining internal balance consume energy steadily, contributing to the sense that energy disappears even when external demands are low. When comparing humans to animals that appear to conserve energy more effectively, it is important to recognize that many species have evolved strategies that reduce cognitive load during periods of inactivity. These strategies allow for lower baseline energy expenditure, particularly in environments where survival depends on conserving resources. Humans, however, evolved in contexts that favored continuous cognitive engagement, even when immediate action was not required. This pattern is reflected in the way the human body responds to modern environments, where cognitive demands can remain high despite reduced physical activity. The resulting experience of fatigue may therefore be less about physical weakness and more about the cumulative cost of sustained neural activity. Understanding this relationship helps explain why human energy can feel limited compared to animals whose energy use is more tightly aligned with immediate physical demands. The human brain's constant activity, shaped by a long history of adaptation to complex and changing environments, remains a central factor in how energy is spent and why it often feels depleted sooner than expected. A costly brain does more than use energy in isolation. It changes the whole economy of the body around it. Once a species begins to rely heavily on memory, anticipation, social reading, and flexible decision-making, energy is no longer divided in the same way it is in many other animals. The brain does not simply add one more expense to the system, it reshapes priorities. In human evolution, this mattered because survival was rarely solved by one narrow behavior repeated under stable conditions. Early humans had to move through landscapes that changed across seasons and longer climate shifts, and they had to do so while depending on group relationships that could support survival or complicate it. Food was not always found in one place, danger did not always come in one form, and success often depended on reading patterns before they became obvious. A body built for that kind of life had to keep energy available for interpretation as well as action. This is one reason human fatigue can feel so different from the visible fatigue of animals. A running animal spends heavily in a moment we can see. A human being may spend heavily in ways that leave little outward trace. Listening, choosing, remembering, restraining emotion, following speech, imagining outcomes, and monitoring the behavior of others all draw on a system that is metabolically active, even in silence. The effect is cumulative. Over the long arc of human origins, this did not make the species weaker in a simple sense. It made the species more dependent on an energy budget that was difficult to simplify. Muscles could not be the only priority, because intelligence was becoming part of the survival strategy. Deep in the human past, this may have supported cooperation during foraging. Careful movement across unfamiliar ground, the use of tools, and the ability to learn from older group members without repeating every dangerous mistake firsthand. These advantages were profound, but they were not free. The body that carries such a brain must support it continuously, and this reduces how cheaply the whole organism can operate. Many animals that appear steadier in their energy use are not necessarily stronger in every general sense. Often they are less burdened by the need to maintain broad, ongoing cognitive and social complexity. Their behaviors may be highly effective, but more tightly constrained. The human path widened the field of possible action, and with that widening came a persistent metabolic burden. This also helps explain why rest in humans is often incomplete. Even when the body stops moving, the mind may continue sorting, predicting, replaying, and preparing. In ancient settings, that tendency may have had clear value. Awareness that lingered beyond the immediate moment could help a person remember a water source, detect tension within a group, or prepare for a seasonal shift in food. In modern settings, the same inherited pattern can feel like unexplained depletion, as if energy is leaking from somewhere hidden. In a sense, it is. It is being used by systems that evolved for a demanding kind of survival, one in which the body had to remain available not only to the landscape, but also to information, memory, and relationship. So when we compare humans with animals and wonder why our energy seems to run out so quickly, the answer is not just that our muscles tire or our habits are poor. It is also that human evolution built a body around a brain that keeps claiming fuel long after visible effort has paused. We are not simply creatures that move through the world. We are creatures that interpret it continuously, and the energy required for that interpretation has been part of the human condition since the beginning of our kind. The question of human energy begins to look different when we consider that the human body is the product of many evolutionary compromises rather than a design aimed at maximum efficiency. Every species carries trade-offs, but the particular combination of traits that defines humans created a body that spends energy in several demanding ways at once. One of the most visible of these trade-offs is upright posture. Walking on two legs freed the hands and changed the way early humans interacted with their surroundings, but it also introduced new mechanical challenges. Balancing the body vertically requires constant muscular adjustments, even during simple standing. Unlike animals whose weight is distributed across four limbs, the human skeleton and muscles must maintain stability in a narrower base of support. This means that even small movements or prolonged standing require subtle but continuous effort from the muscles of the legs, hips, and core. Over long periods, these small demands accumulate and contribute to overall energy use. At the same time, the structure of the human body reflects a history of endurance rather than bursts of extreme strength. Long legs, flexible joints, and the ability to dissipate heat through sweating allowed early humans to travel across long distances in search of food and resources. This endurance-based strategy offered survival advantages, particularly in environments where persistence could compensate for lower speed or strength. However, endurance also requires ongoing energy expenditure, and the human body is not built to shut down that system easily. Even when not engaged in long-distance movement, the underlying mechanisms that support endurance remain active, maintaining muscle readiness and cardiovascular function. These traits, while advantageous in evolutionary terms, contribute to a baseline level of energy consumption that may be higher than that of more specialized animals. Another important trade-off lies in the relationship between strength and flexibility. The human body is capable of a wide range of movements, from fine motor control to complex locomotion, but this versatility comes at the cost of reduced mechanical efficiency in any single action. Animals that specialize in a narrow set of movements often achieve remarkable efficiency, whether in running, climbing, or swimming. Humans, by contrast, maintain a body capable of many different tasks, which requires additional muscular coordination and neural control. This generalist design supports adaptability, but increases the energetic cost of everyday movement. The evolutionary emphasis on adaptability also influenced the way energy is allocated across bodily systems. Rather than maximizing physical power or minimizing metabolic cost, human evolution favored a balance that allowed for complex behavior, social cooperation, and environmental flexibility. This balance is reflected in the distribution of muscle mass, the structure of joints, and the regulation of internal processes such as temperature and metabolism. Each of these systems contributes to survival, but each also requires energy to maintain. The cumulative effect is a body that is constantly managing multiple priorities, often without visible signs of effort. From the earliest stages of human evolution, these trade-offs shaped how energy was used and experienced. The environments in which early humans lived did not reward specialization in a single task, but rather the ability to perform many tasks adequately. This meant that energy was spread across a broad range of functions, reducing the potential for extreme efficiency in any one area. While this strategy supported long-term survival across diverse environments, it also meant that the human body operates with a relatively high baseline energy demand. Understanding these evolutionary compromises helps explain why human energy can feel limited compared to that of animals whose bodies are more tightly optimized for specific ecological roles. The feeling of fatigue, therefore, is not simply a matter of modern lifestyle, but is rooted in the structural and functional choices made over the course of human evolution, choices that continue to shape how energy is spent today. Another trade-off in the human body appears in the way structure and coordination had to evolve together. Standing upright did not simply change the position of the spine or the angle of the hips. It reorganized the entire problem of movement. A four-limbed animal can spread weight across a broader base, often gaining stability almost by default, while the human body must constantly negotiate balance from head to foot. The neck supports a heavy skull above a narrow column. The pelvis must stabilize the trunk during each step, and the feet must absorb force while also preserving forward motion. None of this means that human walking is poorly designed. In many ways, it is remarkably efficient for moderate distance travel. But efficiency in one domain does not erase cost in another. The price of bipedal movement is that many muscles are working quietly, even when the action appears simple. A person standing in place may seem inactive, yet the body is continuously making tiny corrections to remain upright. Those adjustments are small, but over hours and years they belong to the human energy story. In early human environments, this arrangement may have supported a style of life built around scanning open ground, carrying food or infants, using tools, and moving steadily across mixed terrain. These were meaningful advantages. They allowed the body to do more than one thing at once, yet every gain narrowed other possibilities. A body shaped for walking long distances while also freeing the hands could not be equally optimized for raw speed, deep crouch stability, climbing power, and effortless rest in every posture. That is the nature of evolutionary trade-offs. The human form became broadly capable, but broad capability often means constant compromise. This can also be seen in the joints. Human shoulders, hands, knees, and ankles support a wide range of functions, from delicate manipulation to sustained travel. Such versatility is ancient and valuable, but it depends on layers of coordination between muscles, tendons, ligaments, and the nervous system. The more coordination a body requires, the more energy it may spend not only in action, but in preparation for action. Early humans did not live in one narrow mechanical world. They walked, carried, reached, lifted, threw, dug, prepared food, tended fire, and responded to changing terrain. A body that could manage all of this was not a body built around one simple task repeated with perfect efficiency. It was a body built to remain ready across many tasks. That readiness has a cost. Even now, human fatigue often reflects not just effort already spent, but the burden of maintaining a system that must stay poised for many kinds of movement. The same pattern appears in body temperature. Humans rely heavily on internal regulation, especially through sweating and blood flow changes, which helped endurance in warm conditions but also made energy and water management more delicate. Other animals may conserve differently through fur, shade use, posture, or metabolic shifts more tightly matched to their niche. Humans gained unusual mobility and persistence in exchange for a body that must actively regulate itself across diverse settings. So when human energy feels brief beside animal energy, part of the answer lies in the architecture of the species itself. We are living inside a body assembled through layered compromises, where posture, coordination, endurance, hand freedom, and temperature control all support survival, but none come without cost. The farther back we look toward the beginnings of human movement on the landscape, the clearer it becomes that quick fatigue is not separate from our design. It is one of the quiet prices of becoming a creature that could do many things reasonably well, rather than one thing with narrow perfection. The layered compromises that shaped the human body did not emerge from a single moment. but from countless small adjustments across deep time, each leaving behind a pattern that still shapes how energy is used today. The shift toward upright posture changed not only movement, but also how the skeleton distributes force, how muscles support weight, and how the body manages strain. These changes allowed early humans to walk long distances, free their hands, and interact with tools and objects in new ways, but they also created structural tensions that require constant maintenance. The spine must stabilize a tall, flexible structure under the pull of gravity, and the muscles of the back, hips, and legs must continually adjust to maintain balance. These ongoing adjustments consume energy even when no obvious movement is taking place. The joints of the lower body also bear more concentrated stress than in many four-limbed animals, which can distribute load more evenly. This means that the human body must work constantly to maintain alignment and mobility, adding to the background cost of simply existing. At the same time, the demands of endurance influenced how energy is allocated. Human physiology supports sustained activity over time, supported by systems such as sweating and cardiovascular regulation. These adaptations were valuable in early environments where persistence could compensate for a lack of speed or physical dominance. However, the systems that support endurance also require energy to maintain, including circulation, temperature control, and muscle readiness. These systems do not switch off easily, even during rest. Another dimension of this trade-off is flexibility. The human body is capable of a wide range of movements, from precise manipulation to long-distance travel. This versatility requires complex coordination between muscles, nerves, and connective tissues. Maintaining such a system requires continuous input from the nervous system, which itself consumes energy. In contrast, many animals are adapted to narrower ranges of motion that allow for greater efficiency within specific ecological roles. Their bodies can often conserve energy more effectively because their movements and postures are more specialized. Humans, by comparison, carry the cost of maintaining a body that must be ready for many different tasks. This cost is not always visible, but it accumulates steadily. The evolutionary history of humans also reflects a gradual increase in social complexity which further shaped energy use. Social living demands attention, communication, memory, and emotional regulation, all of which draw on the same biological resources that support physical activity. These demands were not separate from survival, they were integral to it. Cooperation, shared knowledge, and group coordination increased survival chances, but they also added to the energetic burden carried by each individual. The result is a species whose energy is distributed across a broad array of functions, many of which operate continuously and outside of conscious awareness. This distribution helps explain why human energy can feel limited even in the absence of intense physical effort. The human body was not optimized solely for energy conservation, but for a balance between adaptability, endurance, coordination, and social engagement. This balance supported survival across varied environments, but also created a system in which energy is rarely idle. When comparing humans to animals that appear to conserve energy more effectively, it becomes clear that the difference lies not in simple strength or weakness, but in the underlying design shaped by evolutionary trade-offs. The human body carries the legacy of these trade-offs in its structure, function, and energy use. Understanding this context allows us to see human fatigue not as a flaw, but as part of a broader biological story that began long before modern life and continues to influence how energy is experienced today. The human body did not evolve to be the fastest, strongest, or most mechanically efficient body in the animal world, yet it did evolve for a kind of endurance that made survival possible across long distances and uncertain landscapes. This can seem confusing at first. If humans were shaped in part for endurance, why does human energy now feel so brief, so fragile, and so easily spent? The answer begins with a distinction between endurance and effortless efficiency. Endurance is not the same as cheap movement. It is often the ability to keep going by distributing cost over time, accepting slower pace, steady heat, and continuous fuel use rather than depending on explosive power. Early humans may have benefited from this kind of movement in open or shifting environments, where walking, tracking, carrying, and returning mattered more than winning a short burst of speed. In that setting, the body was not built to conserve every drop of energy in stillness the way some animals do. It was built to remain capable of prolonged activity under changing conditions. That ability was valuable, but it came with a price. A body adapted for repeated travel on two legs must maintain posture, joint alignment, temperature control, and muscular coordination across long spans of time. Even before obvious fatigue arrives, energy is already being spent on these quiet supports. Many animals that seem tireless beside us are using a different strategy. They may move with extraordinary economy inside a narrower behavioral range, or they may alternate sharply between rest and intense action. A grazing animal can often feed while moving slowly through a familiar pattern. A predator may save its energy for a decisive attempt. A bird may travel with a body shaped specifically for one form of motion. Human endurance was broader and more flexible, but less specialized. It depended not only on the legs and lungs, but on memory, planning, tool use, cooperation, and persistence through discomfort. That means human energy was never just muscular energy. From the deeper beginning of our species, movement was tied to information. To travel far and survive, people had to remember routes, anticipate water, read weather, monitor companions, and adjust pace to circumstance. This widened the cost of endurance itself. The body was not simply carrying weight across land. It was carrying attention across uncertainty over many generations that may have favored bodies capable of sustained effort, but not bodies that could shut down unnecessary expenditure as completely as some other animals. The modern feeling of quick exhaustion may partly reflect the loss of the conditions that once gave this endurance pattern its meaning. Human movement in the past was often woven into daily survival. It had rhythm, purpose, and environmental feedback. Modern life often keeps the underlying energy system but removes the older pattern of use. The body still pays for posture, regulation, and readiness, yet movement may come in fragments, and mental demand may continue without the balancing effect of steady physical action. This does not mean early humans lived effortlessly or that they possessed endless stamina. It means their endurance was embedded in a way of life that matched the body more closely than many modern routines do. When we compare ourselves with animals and wonder why they seem to keep their energy longer, we may be seeing not greater overall power, but a better fit between body design and daily behavior. Humans evolved as flexible endurance generalists, and generalists often pay more to stay ready. So the paradox begins to sharpen. The same long human story that gave us the capacity to travel, persist, and adapt may also help explain why our energy now feels so quickly drained, because the body we inherited was built to keep going through uncertainty, not to feel effortless inside comfort. The way humans spend energy during movement becomes clearer when we compare how different bodies handle distance, load, and rhythm. Many animals move in ways that minimize unnecessary effort. Their strides, postures, and muscle use are tuned to the specific demands of their environment, and this tuning reduces the amount of energy required to travel or to wait. A four-legged animal, for example, spreads weight across a stable frame, allowing movement with less continuous muscular correction. A bird in flight can glide when air currents allow, reducing effort between bursts of wing beats. In contrast, human movement relies on a balance that must be maintained actively at nearly every moment. The human body stands upright on two legs, placing more responsibility on fewer joints and muscles to control stability. Even slow walking requires constant coordination between the hips, knees, ankles, and spine, and this coordination draws on energy whether the movement is fast or slow. The endurance capacity of humans allowed early groups to move across varied terrain in search of food, water, and safety, but this ability did not come without cost. Maintaining balance, regulating body temperature, and coordinating movement over long periods all require sustained energy use. This means that even activities that feel moderate can gradually accumulate into significant fatigue. The pattern of human movement is also influenced by how tasks are layered. In many animals, movement is often closely tied to a single purpose, such as feeding or escaping danger. In humans, movement frequently occurs alongside other demands, including carrying tools, monitoring the environment, and coordinating with others. These combined demands increase the overall energy cost of what might appear to be simple activity. Over time, the human body adapted to support this complex pattern of behavior, but adaptation does not remove the energetic expense. Instead, it distributes energy across multiple systems that must work together. The cost of movement is therefore not limited to the muscles alone, but includes the nervous system, sensory processing, and internal regulation. In early human environments, these layered demands supported survival in landscapes that required flexibility rather than specialization. However, they also created a baseline level of energy expenditure that remains part of human biology today. The comparison with animals highlights how different evolutionary paths shape energy use. Many animals achieve impressive feats of movement, but often within narrow ranges of behavior that allow for efficient energy use. Humans, by contrast, maintain a body capable of varied actions, from long-distance travel to precise manipulation, and this versatility increases energy demands even when tasks seem ordinary. The feeling of fatigue after what appears to be moderate effort can therefore reflect the cumulative cost of maintaining a versatile and responsive body. When considered over long periods, this pattern helps explain why human energy can feel quickly depleted. It is not simply a matter of weakness or inefficiency, but a consequence of a body designed to manage complex and overlapping demands. This understanding reframes the experience of fatigue as part of a broader evolutionary pattern rather than a simple shortcoming. The same traits that allowed humans to endure uncertain environments, travel across diverse landscapes, and coordinate complex tasks also shaped a system that uses energy continuously, often in ways that are not immediately visible. Recognizing this connection helps clarify why human energy may appear to run out more quickly than that of animals whose bodies are optimized for narrower, more predictable patterns of movement. The endurance pattern of the human body becomes clearer when we consider how long movement, posture, and coordination interact over time. In many animals, physical activity occurs in short, clearly defined phases, with extended periods of stillness that allow the body to recover and preserve energy. A predator may wait for hours before a brief chase, or a grazing animal may alternate slow movement with long rest, allowing energy reserves to stabilize. Humans evolved with a different rhythm. The body was shaped to sustain moderate effort across long durations, often without clear pauses. Early humans may have traveled for hours across varied terrain, scanning the horizon, tracking subtle changes in the landscape, and carrying tools or food. This form of endurance did not rely on sudden power, but on the ability to continue through discomfort. While this capacity supported survival, it also created a steady drain on energy that did not easily resolve into rest. The human body maintains readiness even when still, keeping muscles prepared to stabilize posture, adjust balance, and resume movement at any moment. This background readiness draws energy continuously, meaning that the boundary between effort and rest is less clear than in many animals. Over time, this pattern became deeply embedded in human physiology. The cardiovascular system supports long periods of moderate activity, while the musculoskeletal system maintains alignment and responsiveness. These systems do not fully disengage during inactivity, contributing to a persistent baseline of energy expenditure. In contrast, many animals possess physiological mechanisms that allow for deeper energy conservation during periods of inactivity, such as significant reductions in metabolic rate or more complete muscular relaxation. These mechanisms enable extended periods of recovery that are less accessible to humans. The difference is not simply a matter of will or habit, but reflects distinct evolutionary strategies. Humans gained the ability to persist across unpredictable environments, but this flexibility required a body that rarely fully shuts down. The experience of fatigue can therefore emerge not only from intense exertion, but from the cumulative cost of remaining prepared. In early human societies, this constant readiness supported survival by enabling quick responses to changing conditions, coordination with others, and sustained travel. However, the same traits that supported survival also increased the likelihood of gradual energy depletion. Modern life often amplifies this pattern. Many people experience fatigue despite limited physical activity, in part because the body continues to operate according to ancient patterns of readiness. Mental demands, emotional regulation, and social engagement layer additional costs onto the baseline energy expenditure required to maintain posture, balance, and internal stability. When compared with animals that can more readily reduce activity or enter states of deep rest, the human body appears less efficient in conserving energy. Yet this apparent inefficiency is inseparable from the evolutionary path that allowed humans to adapt to diverse environments and complex social structures. The sense that human energy runs out quickly is therefore not a simple mismatch between modern life and ancient biology, but a reflection of long-standing patterns of energy use that favored persistence, flexibility, and awareness. Understanding this context helps reframe fatigue as part of a broader biological narrative rather than a simple failure of strength. The human body was not built to excel at narrow efficiency, but to sustain activity across a wide range of demands, and that design continues to shape how energy is spent and how exhaustion is felt. Food is the most visible source of energy in human life, yet the way humans obtain, process, and depend on food differs in important ways from many animals. At the surface, eating appears simple. Fuel enters the body, and the body uses it. But the real story is more complex. The energy available to any living creature depends not only on what is eaten, but on how reliably it can be obtained, how efficiently it can be digested, and how predictably it can be used. Many animals occupy narrow ecological roles that link their energy intake closely to a specific food source. A grazing animal feeds on abundant plant matter in environments where such food appears regularly. A predator may rely on a specific type of prey, whose behavior, migration, and vulnerability follow patterns shaped by season and terrain. These animals face risk, but their energy intake often follows a stable rhythm that allows their bodies to tune metabolism to predictable availability. Humans took a different path. Early human ancestors did not rely on one stable food source. They consumed a shifting mixture of plants, seeds, tubers, small animals, and whatever could be obtained through opportunity and skill. This broad diet was a strength, because it allowed survival across changing landscapes. Yet a broad diet also creates uncertainty. When food is not guaranteed in one form, the body must remain prepared to shift strategies, and that readiness requires energy. For humans, food acquisition was not only a matter of consuming calories, but also of searching, remembering locations, evaluating risks, processing foods that were difficult to digest, and cooperating with others to secure resources. All of these steps carry energetic cost before food even reaches the body. Unlike many animals that feed in patterns tightly matched to their anatomy and habitat, humans expanded their range of possible foods through tools, social coordination, and eventually fire. These changes improved survival, but they also introduced new layers of energy expenditure. Gathering, hunting, carrying, preparing, and sharing food became parts of the energy cycle, not separate from it. Even the act of making food digestible required effort, from breaking tough fibers to processing hard materials. While these practices eventually increased the amount of energy that could be extracted from food, they did not eliminate the costs involved in obtaining it. The energy gained from food, therefore, sits at the end of a long chain of activity rather than at the beginning. In this sense, human energy depends not only on what is eaten, but on the entire process of making food available and usable. This distinguishes humans from many animals whose feeding strategies involve less complex preparation. The variability of food sources also meant that human bodies evolved to handle fluctuation rather than stability. Energy storage, metabolism, and hunger signals reflect a history in which food availability changed across seasons and regions. The body, therefore, operates with systems designed to buffer uncertainty, which can sometimes feel like instability in modern life where food may be more available but less aligned with older biological patterns. This context helps explain why human energy can feel unpredictable. The body is not only reacting to what is eaten in the present moment, but also to deeply ingrained patterns shaped by environments where food was irregular and often hard-won. Understanding this helps clarify why fatigue can arise even when eating seems adequate, and why human energy cannot be understood solely through simple comparisons of calorie intake. It reflects a long history in which survival depended on flexibility in diet, persistence in acquisition, and the capacity to process a wide range of foods under changing conditions. The way humans process food after it is found adds another layer to the story of energy use. Many animals eat foods that match their digestive systems with remarkable precision, allowing them to extract energy with relatively low additional cost. Herbivores often have specialized digestive tracts that break down plant fibers slowly and efficiently. supported by gut microbes that convert otherwise unusable material into usable energy. Carnivores consume concentrated sources of protein and fat, reducing the need for complex preparation. Their bodies are adapted to handle specific kinds of nutrients with minimal extra processing. Humans, by contrast, evolved along a more complex nutritional path. The human diet became varied, incorporating plants, animal matter, and eventually cooked foods. This flexibility helped early humans survive in diverse environments, but it also introduced a broader range of digestive demands. Processing different types of food requires energy, from breaking down fibrous plants to metabolizing fats and proteins. The digestive system must adjust enzyme production, regulate absorption, and coordinate with the rest of the body to manage fluctuating inputs. These processes occur continuously after eating and contribute to the ongoing use of energy. The development of cooking marked a major shift in how humans obtained energy from food. Cooking can make certain nutrients easier to access and reduce the energy required for digestion, but it also added new steps to the energy cycle. Gathering fuel, tending fire, and preparing food all required effort before the benefits of increased caloric availability could be realized. These behaviors became part of the human way of life, shaping how energy was spent and gained. While cooking increased the efficiency of nutrient extraction in many cases, it did not remove the underlying costs associated with acquiring and preparing food. The reliance on a diverse diet also meant that human bodies had to maintain systems capable of handling a wide range of nutrients. This versatility supports survival across changing environments but can reduce efficiency compared to animals with highly specialized diets. For example, a species adapted to a single abundant food source can often optimize digestion and energy storage around that resource, whereas humans must remain capable of processing many types of food, each with different energetic implications. This flexibility requires regulatory systems that monitor nutrient levels, manage storage, and balance immediate needs against future demands. These systems operate continuously and draw on the body's energy supply. In early human societies, food availability was rarely constant. Periods of abundance could be followed by scarcity, requiring the body to adjust metabolism accordingly. Mechanisms that promote storage during times of plenty and conservation during scarcity evolved as adaptive responses to this variability. However, these mechanisms can also contribute to fluctuations in perceived energy levels, especially when environmental conditions change rapidly or unpredictably. The relationship between food intake and energy output is therefore not straightforward. It is shaped by the quality of food, the effort required to obtain it, the complexity of digestion, and the body's ongoing efforts to maintain internal balance. Unlike animals whose energy intake often aligns closely with their metabolic design, humans operate within a broader and more variable system. This complexity helps explain why energy levels can feel inconsistent even when food intake appears sufficient. The human body is not simply converting calories into motion, it is managing a dynamic and multifaceted process shaped by evolutionary history. Recognizing this helps place modern experiences of fatigue within a larger context, where energy is not only consumed by movement, but also by the systems that process, regulate, and distribute the fuel that sustains life. The final layer of the food question is not only what humans eat or how humans digest it, but how uncertain food shaped the entire rhythm of human energy. Many animals live inside feeding systems that are narrow but stable enough for the body to anticipate what will come next. Their hunger, movement, rest, and digestion often fit into cycles that repeat with relative consistency, even when conditions are harsh. Human beings inherited something less settled. From deep in the human past, food was often tied to variation in season, place, memory, skill, and cooperation. A useful plant might be available only for a limited time. A landscape that provided well in one period could become far less generous in another. A successful day of gathering or hunting could be followed by a leaner stretch. This did not make human life uniquely miserable, and it does not mean that prehistory was a constant emergency. But it does suggest that the human body evolved in relation to fluctuation rather than perfect regularity. That matters because a body shaped by fluctuation does not simply burn energy according to what is present in the moment. It also carries older patterns of storage, caution, appetite, and internal redistribution. Energy use in humans is therefore tied to uncertainty at a much deeper level than the modern meal. The body must decide whether to spend, store, slow, repair, or remain ready, and these decisions are influenced by systems that were shaped when food was not always immediate or predictable. In this sense, human fatigue can never be explained only by how much food is eaten. It is also connected to how the body interprets availability. Many animals whose food matches a specialized niche may be able to operate within tighter biological expectations. Their feeding strategy and metabolic strategy often reinforce one another. Humans followed a broader path. That breadth was powerful because it allowed survival across many ecologies, but it also meant that the body had to remain adaptable across many kinds of fuel and many kinds of scarcity. Adaptability can protect survival, yet it rarely feels simple from inside the body. This helps explain why human energy can feel uneven. The same species that learned to widen its diet through tools, memory, fire, and social coordination also became a species whose fuel system was stretched across many layers of effort. Food had to be found, recognized, shared, sometimes processed, and then absorbed by a body that was already paying for brain activity, temperature control, posture, and group life. By the time energy becomes available for action, much has already been spent elsewhere. Early humans may have managed this within ways of living that matched the body more closely, because searching, preparing, moving, and eating were woven into one continuous rhythm. In modern settings, the older logic of the body remains, but the rhythm is often broken. Food may be easier to obtain while mental strain remains high, movement becomes irregular, and internal signals become harder to interpret. Even without turning to modern explanations too quickly, the older point remains clear. Human energy was shaped by a long relationship with variable food and variable effort. That relationship rewarded flexibility more than narrow efficiency. So when we compare ourselves with animals and wonder why our energy seems to vanish more quickly, part of the answer lies in the long food history of our species. We did not evolve around one stable source, one stable rhythm, or one simple metabolic pattern. We evolved around the need to keep going through changing conditions, using a body that could store, adapt, process, and endure. But that very breadth made human energy less smooth, less economical, and more vulnerable to the feeling of running low, even when survival itself had once depended on exactly that flexible and costly design. One reason human energy seems to run out so quickly compared to animals is that humans became a species able to live in places that no single body plan was perfectly built for. Many animals survive by fitting tightly into one ecological pattern. Their food, movement, shelter, and daily rhythm often match a narrower range of conditions, which allows the body to conserve energy by specializing. Humans followed a more difficult path. Over a long span of evolution, our ancestors moved through forests, open grasslands, cold edges of glacial worlds, dry regions, coasts, river valleys, and eventually almost every major habitat on Earth. This did not happen because the human body was the most efficient body in each place. It happened because the human body, together with human behavior, could adapt broadly enough to keep functioning in many places without being perfectly optimized for any one of them. That broad adaptability was powerful, but it came with a cost. A body that must tolerate different climates, different diets, different movement demands, and different social arrangements often carries higher baseline expenses than a body matched to one stable niche. Human skin, body hair, sweating, fat storage, posture, hands and brain all belong to this story. None of these traits works in isolation. Together they form a flexible package, one that allowed survival through adjustment rather than narrow perfection. Yet adjustment requires constant regulation. In a cold place, the body must work to preserve heat. In a hot place, it must work to release heat. With unfamiliar foods, the body must process and respond carefully. In difficult landscapes, the body must change pace, posture, and effort. All of this draws on energy. Many animals also adapt, of course, but often within stricter limits. A species shaped for one climate or one feeding pattern may perform with remarkable efficiency as long as those conditions remain present. Humans gained something different. We gained range. That range depended not only on flesh and bone, but on memory, learning, cooperation, and the transfer of knowledge across generations. From early in human life, Survival in a new place was rarely just a matter of walking into it. It required knowing where water might be found, when food was available, how weather changed, which shelters worked, and how the group could respond together. In this sense, adaptability itself became part of the human energy burden. The body was not only paying for heat, movement, and digestion, it was also paying for the cognitive and social systems that made adjustment possible. This helps explain why the human body can feel easily drained even when compared with animals that appear more stable in their energy. Those animals may be living within a tighter fit between body and habitat. Humans, by contrast, often carry the metabolic price of staying ready for variation. The farther back we look toward the beginning of human expansion, the clearer this becomes. Our ancestors did not succeed because they escaped biological cost. They succeeded because they could bear a broader set of costs and continue functioning across shifting conditions. That is a very different kind of strength. It is not the strength of perfect efficiency. It is the strength of tolerating mismatch and compensating for it through flexibility. In modern life, this old pattern can feel like unexplained fatigue, as if the body is spending more than it should. In one sense, it is. But that spending reflects a long evolutionary history in which human survival depended on carrying a body that could keep adjusting instead of settling into one narrow, economical design. And that ancient advantage may be one reason human energy still feels so easy to lose beside the steadier economy of many animals. Adaptability sounds like a gift, and in evolutionary terms it was, but gifts of this kind are rarely free. A body that can function across many environments must keep more systems available at once, and each available system carries an energy cost. Human beings did not evolve thick fur for one cold niche, a specialized stomach for one food source, or a fixed locomotion pattern for one narrow terrain. Instead, the human body remained comparatively open-ended. It could walk long distances, handle varied diets, regulate heat through sweating, use hands for tools, and rely on learning to compensate where anatomy alone was not enough. This broad usefulness made expansion possible, yet it also meant that the body had to manage more uncertainty internally than many animals do. A specialized animal often meets the world with a narrower set of biological expectations. If its habitat, food, and timing remain within familiar limits, the body can operate with impressive economy. Humans rarely lived inside that kind of tight match. From the deeper beginnings of our species, conditions could shift across seasons, landscapes, and generations, and survival depended on staying adjustable rather than staying perfectly fitted. That adjustability demanded constant physiological work. The body had to regulate hydration in heat, conserve warmth in cold, recover from long movement, tolerate mixed foods, and support a brain that could learn new local patterns. None of these demands was separate from energy. They were energy. The ability to enter a new environment and remain viable often depended not on one ideal human body, but on a body willing to pay continuous costs while behavior, memory, and cooperation filled the gaps. This is why adaptability can make human energy feel unstable. A broadly adaptable body is not always an economical body. It is often a body holding several possibilities open at once. Early humans moving into unfamiliar regions may have needed to test foods cautiously, alter travel routes, change shelter habits, and coordinate more closely with others. These responses increased survival, but they also widened the field of expenditure. In many animals, ecological success comes from narrowing. In humans, it often came from widening. Widening meant more knowledge, more adjustment, more regulation, and therefore more metabolic burden. This pattern did not disappear once a place became familiar. Human social life itself kept the adaptive system active. Children had to learn local conditions. Groups had to preserve knowledge through memory and teaching. Individuals had to remain sensitive to shifts in weather, resources, and relationships. The body was living not only in a physical environment, but in a learned environment. And learned environments are costly because they depend on cognition, attention, and repeated behavioral flexibility. This helps explain why human fatigue can arise even without obvious physical strain. The old adaptive burden remains partly invisible. A person may simply feel that energy is drained away, while much of that energy has gone into regulation, interpretation, and readiness, rather than direct muscular effort. Compared with animals whose bodies fit more tightly to one ecological role, the human body may seem inefficient. Yet this apparent inefficiency was part of what allowed our ancestors to survive in places where a narrower design might have failed. Human beings did not become a species of low-cost endurance. They became a species of expensive flexibility. The farther back we look toward the scattered origins of human life across difficult and changing landscapes, the clearer it becomes that our quick fatigue is tied not only to modern stress or habit, but to an ancient biological strategy in which survival depended on paying more energy in order to remain adaptable when the world refused to stay the same. The cost of human adaptability becomes most visible when we see that adaptation is never only a trait of the body, it is also a trait of time. Many animals are closely shaped by recurring patterns in a particular habitat, so their energy use can settle into rhythms that are repeated with relative consistency across days and seasons. Humans entered a different relationship with time because survival often depended on preparing for conditions that were not yet present. A group might need to remember where water remained when a season changed, how cold returned to a certain valley, when a coastline offered more food, or when a familiar place became less reliable. This kind of survival required more than physical tolerance. It required carrying the past into the present and the future into the body's decisions. That ability widened human power, but it also widened human energy use. A body that must live through memory and anticipation cannot conserve energy as simply as a body that responds mainly to immediate cues. From deep in the human past, adaptation meant maintaining systems that could learn, compare, predict, and adjust. The nervous system had to remain responsive not only to what was happening now, but also to what might happen soon. The social world intensified this further. Early humans did not adapt as isolated individuals. They adapted in groups, through shared knowledge, imitation, teaching, and coordinated action. That meant energy was spent not only on keeping one body alive in one environment, but on staying synchronized with other people whose behavior affected survival. A person had to attend to mood, trust, timing, and cooperation as much as to weather and terrain. These social demands were not additions to biological life. They became part of biological life. Animals also live socially in many cases, but the human form of social adaptation appears to have become unusually dependent on learning and flexible coordination across generations. This made human success more portable, yet it also made the energy burden more complex. The body was no longer paying only for movement, digestion, and temperature control. It was also paying for culture in its earliest forms, for the storage and transfer of practical knowledge, for the regulation of behavior inside a group, and for the mental effort of adjusting when old patterns no longer worked. The result is that human energy often feels consumed by things that leave no simple physical trace. A person may remain seated and still be metabolically engaged in a struggle to interpret, remember, anticipate, restrain, and align. This does not mean that prehistoric people were lost in constant overthinking, and it does not mean every ancient environment demanded the same kind of mental effort. It means only that the human strategy of survival relied increasingly on flexible adaptation carried through time and through shared knowledge, and that strategy was energetically expensive. This helps explain why the human body can seem less smooth and economical than the bodies of many animals. A specialized creature can often rest more completely because the world it is built for asks less variation from it. Humans, by contrast, became a species that often survived by bridging gaps between body and environment through learning and adjustment. Those gaps cost energy. The farther back we follow the human story, the clearer it becomes that our species did not escape limitation by becoming cheap to run. It survived by becoming broad, responsive, and historically aware in ways that kept more internal machinery active. So when human energy seems to run out quickly compared to animals, part of the answer lies here. We are not only using energy to live in a place, we are using energy to adapt across places, across seasons, across relationships, and across remembered change. And that ancient burden may be one reason the human body so often feels as though it is spending more than it can comfortably keep. Human energy does not operate only within the body. It is deeply shaped by the social world that surrounds it. Unlike many animals that can live relatively independently once they reach maturity, human beings evolved within systems of cooperation where survival depended on relationships, communication, and shared effort. From the earliest known human groups, individuals rarely survived alone for long periods. Food gathering, tool-making, childcare, defense, and the transmission of knowledge all required interaction with others. This created a way of life in which energy was not spent solely on individual survival tasks, but on maintaining social bonds, managing conflict, interpreting behavior, and coordinating action. These activities do not always appear physically demanding, yet they draw continuously on mental and emotional energy. A human watching the expressions of others, judging trust, negotiating status, or maintaining group cohesion is engaging biological systems that consume energy just as surely as walking or lifting. Many animals also live in groups, but the degree of social complexity varies widely. In some species, social interactions are relatively fixed, guided by stable hierarchies or simple patterns of cooperation. In humans, social life became far more flexible and layered. Relationships were not limited to immediate kin or narrow roles. They extended across shifting alliances, shared memories, and cultural practices that could change over time. This required individuals to track not only who was present, but how relationships evolved, how reputations formed, and how cooperation might succeed or fail. These demands required cognitive effort, and cognitive effort requires energy. In early human environments, social awareness could directly affect survival. Cooperation could determine access to food, protection from danger, and support during illness or injury. As a result, the human nervous system became tuned to social cues, maintaining sensitivity to facial expressions, tone of voice, body language, and subtle changes in group dynamics. This constant monitoring is metabolically costly, even when it occurs outside conscious awareness. Unlike animals whose social structures may rely on simpler signals or more rigid patterns, humans must often interpret ambiguity and adjust behavior accordingly. This flexibility enhances adaptability but increases energy use. The connection between social life and energy becomes clearer when we consider that social exclusion or conflict can be experienced as a biological stressor. The body responds to social tension through hormonal and neurological pathways that affect heart rate, metabolism, and immune function. These responses consume energy, even when no physical threat is present. In this way, social complexity becomes an invisible but persistent component of human energy expenditure. Over long periods of evolution, this pattern shaped not only behavior but physiology. The human body and brain became adapted to environments where group living was central, and this adaptation created ongoing energy demands. In modern contexts, social interaction has changed form but not disappeared. Communication now extends through language, symbols, and technology, adding new layers of cognitive and emotional engagement. These forms of interaction may not require physical exertion, yet they continue to draw on the same biological systems that evolved to manage social relationships in earlier human environments. This helps explain why people can feel drained after periods of intense social engagement, decision-making, or emotional regulation, even in the absence of physical labor. When comparing humans to animals, it becomes important to recognize that energy is not spent only through movement or metabolism, but also through the maintenance of complex social systems. Many animals conserve energy by operating within simpler or more stable social structures, while humans expend energy navigating dynamic and intricate social landscapes. This difference reflects an evolutionary path in which survival depended not only on physical ability, but on the capacity to live within and manage complex social worlds. The result is a species whose energy is continually shaped by relationships, communication, and shared life, contributing to the sense that human energy can be depleted in ways that are less visible but no less real. The social life of humans does more than add extra activity to an already busy body. It changes what the body must remain prepared for. In many animals, group life certainly matters, but the rules of that life are often narrower, more repetitive, and more directly tied to immediate conditions such as mating, feeding, or defense. Human groups became something more demanding. They were not only clusters of bodies sharing space, they were moving networks of obligation, memory, expectation, and learned behavior. To live inside such a network required constant adjustment. A person had to remember who had helped before, who could be trusted, who was vulnerable, who held knowledge, and when cooperation had to take priority over individual impulse. These are not abstract additions to survival. They became part of survival itself. In early human settings, a body did not simply need enough energy to walk, carry, and endure weather. It also needed enough energy to remain socially legible to others, to read changing moods, to respond to tension without destroying cohesion, and to participate in the shared timing of group life. This is one reason human fatigue can feel out of proportion to visible action. Much of the work is relational. Even silence inside a group can be active. Watching faces, sensing approval or danger, restraining reaction, and choosing words or gestures all draw on a nervous system built for complex coordination. The farther back we look toward early human life, the more likely it is that this social burden was not optional decoration around biology, but one of the main conditions under which biology had to operate. A solitary body can conserve in ways a deeply social body cannot. A social body must stay available to others. It must remain responsive, interpretable, and connected. This availability costs energy. It also widens the range of things that can exhaust a person. Physical movement is only one part of the human bill. Waiting for someone's decision, carrying responsibility for children or older members, learning patterns of cooperation, and adapting behavior for group stability all consume fuel in quiet ways. Many animals live socially with impressive coordination, but human social life became unusually dependent on flexible learning rather than mostly fixed patterns alone. That meant each generation had to absorb practical knowledge through observation, imitation, and teaching. Knowledge itself became part of the shared survival system. Yet storing, recalling, and transmitting knowledge requires attention, and attention is metabolically costly. The body was therefore paying not only for individual maintenance but for participation in a collective memory. This helps explain why human energy does not behave like a simple mechanical reserve. It is entangled with belonging. Even in the deep past, to fall out of rhythm with the group could bring real danger, so the human organism became sensitive to signals that many animals may process more narrowly. This sensitivity was useful, but it also made human life expensive from the inside. The body learned to care about things that do not weigh anything in the hand: reputation, timing, loyalty, shared meaning, and emotional tone. These are ancient costs, not merely modern ones. Modern life may intensify them, but it did not invent them. When we compare ourselves with animals that appear calmer or less drained, we may be overlooking the fact that many of them are not carrying the same kind of social load. Human beings survive not only through muscle and digestion, but through delicate and ongoing coordination with other minds. That coordination can preserve life, spread knowledge, and soften hardship, yet it also helps explain why human energy seems to disappear so quickly. We are not only feeding a body that moves through the world, we are feeding a body that must remain tuned to relationship, shared memory, and the fragile demands of living together. And that long social inheritance may be one of the quiet reasons our energy so often feels easier to lose than the energy of many other animals. The weight of human social life does not appear only in moments of conflict or cooperation, but in the quiet background processes that never fully turn off. Even when no immediate threat or negotiation is present, the human nervous system continues to simulate possibilities, rehearse interactions, and maintain an internal model of the social world. This persistent activity can make the human experience of rest feel incomplete, as if part of the mind remains on watch even when the body is still. In many animals, social structures are important but often operate within relatively fixed patterns that reduce the need for continuous interpretation. A herd may move together based on simple cues, or a dominant structure may remain stable for long periods, reducing the need for constant recalculation. Human groups, by contrast, have historically been more fluid. Roles could shift, alliances could change, and survival could depend on reading subtle signals within the group. This fluidity required individuals to remain sensitive to nuance, which in turn required ongoing cognitive effort. The energetic cost of this effort is not always recognized because it rarely appears as visible labor. A person may feel tired after a day spent mostly in conversation, observation, or decision-making, even though the body has not performed intense physical work. This reflects the reality that energy is consumed not only by muscles but also by the processes that maintain social awareness and emotional balance. Early human environments likely reinforced this pattern. In small groups where cooperation was essential, misreading a situation could carry significant consequences. As a result, the brain evolved to prioritize social information, maintaining vigilance even in the absence of immediate danger. This trait helped early humans navigate complex group dynamics, share resources, and coordinate action, but it also contributed to a constant background expenditure of energy. Over generations, this pattern became part of human biology, shaping how energy is used and how fatigue is experienced. In modern life, the scale and pace of social interaction have changed, but the underlying systems remain. Communication now occurs through language, symbols, and technology, often requiring sustained attention and emotional regulation. These demands can accumulate over time, contributing to a sense of exhaustion that is not easily explained by physical activity alone. When comparing humans to animals that appear less affected by such demands, it is important to consider that many species operate within narrower social frameworks that require less continuous adjustment. Their energy use may therefore appear more efficient, even if their lives involve significant physical challenges. The human experience of fatigue, by contrast, reflects a broader set of demands that include both physical and social dimensions. This does not suggest that human life is inherently more difficult than that of other species, but rather that the nature of human adaptation has created a distinct pattern of energy use. By carrying the costs of complex social life alongside the demands of physical survival, the human body operates within a system that rarely allows energy to be fully conserved. Understanding this helps explain why energy can feel depleted even when physical demands are low, and why comparisons with animals must account for differences in social complexity as well as physical capacity. The human story is therefore not simply one of greater effort or lesser endurance, but of a different kind of energetic balance shaped by the need to live not only in a physical world, but also in a social one, where attention, memory, and emotional regulation are as central to survival as movement or strength. The modern world appears to have solved many of the physical challenges that once defined human survival, yet the experience of running out of energy has not disappeared. In fact, for many people, it has become more confusing. Compared with early human life, the modern environment often requires less direct physical effort for basic survival. Food is more accessible, shelter more stable, and immediate physical threats less frequent. Yet fatigue remains widespread, suggesting that the relationship between effort and exhaustion is not straightforward. One reason lies in the way technology has altered the balance of human activity without changing the underlying biology. Tools, machines, and digital systems have reduced the need for certain forms of physical labor, but they have not reduced the body's baseline energy demands. The systems that evolved to support movement, vigilance, and social coordination remain active, even when daily life involves less physical strain. At the same time, modern environments introduce new forms of demand that draw heavily on cognitive and emotional systems. Attention must be sustained across complex tasks. Decisions must be made rapidly, and social interactions extend beyond immediate physical presence through communication technologies. These demands can be continuous and diffuse, lacking the clear boundaries that once defined periods of exertion and rest. As a result, energy is often consumed steadily throughout the day, even in the absence of obvious physical effort. This can create the impression that energy drains quickly for no clear reason. Another factor is the mismatch between the body's evolved rhythms and modern patterns of activity. Human physiology developed in contexts where periods of movement, rest, and food intake followed environmental cues such as daylight, temperature, and resource availability. Modern life often disrupts these rhythms, with irregular sleep patterns, prolonged periods of sitting, artificial lighting, and continuous cognitive engagement. These conditions can interfere with the body's natural regulation of energy, leading to feelings of fatigue that do not align with actual physical expenditure. Unlike many animals that maintain consistent patterns of activity closely tied to environmental cycles, humans often live in ways that place sustained demands on attention and regulation. This ongoing demand can prevent the deep recovery that would otherwise restore energy reserves. The result is not simply physical tiredness, but a broader sense of depletion that reflects the combined load on multiple systems. It is important to recognize that this pattern is not entirely new. The human body has long operated with a high baseline energy cost due to the demands of cognition, coordination, and adaptability. What has changed is the context in which these demands occur. Modern environments often reduce opportunities for natural recovery, while increasing the duration and intensity of cognitive and social demands. This combination can amplify the perception of energy loss, even when basic survival needs are more easily met. The contrast with animals highlights this dynamic. Many animals still live within environmental rhythms that allow for clear periods of activity and rest, and their energy systems remain closely aligned with these patterns. Humans, by contrast, often experience prolonged activation without corresponding periods of restoration. Understanding this mismatch helps clarify why energy can feel scarce in modern life, not because the human body is fundamentally flawed, but because it operates within conditions that differ sharply from those under which it evolved. The sense of quickly running out of energy is therefore linked not only to biological design, but also to the interaction between that design and the environments humans have created. Technology did not remove the ancient cost of being human, it changed where that cost appears. In earlier human settings, energy was often spent in visible ways through walking, carrying, building, gathering, watching the weather, tending fire, and adjusting to the land. In modern life, much of that visible labor has been reduced or displaced. Yet the body itself has not become a cheaper organism to run. The brain still draws energy continuously, the muscles still maintain posture, the nervous system still monitors the environment, and the social mind still reacts to signals of expectation, approval, urgency, and threat. What technology often does is shift human expenditure away from the landscape and into sustained attention. A person may now sit still for long periods and feel as drained as if something heavy had been carried, because the burden has moved into perception, decision-making, emotional restraint, and constant low-level response. This shift can be deceptive. Machines appear to save human energy, and in one narrow sense they do, because fewer people must perform the same amount of physical work by hand. But the energy that was saved in muscle is often reclaimed by other demands. The day becomes filled with tasks that require interruption, judgment, memory, and prolonged mental readiness. Human beings were never only muscular creatures, yet modern conditions can force the older cognitive burden to run almost without relief. In the deeper human past, attention moved with the rhythms of place. A person watched the path, the sky, the group, the season, and the signs of food or danger. Those demands were real, but they were embedded in environments that also offered clearer pauses, clearer boundaries, and more direct links between effort and outcome. Modern systems often weaken those boundaries. Information arrives without rest, decisions multiply faster than the body can settle, and the nervous system remains engaged in problems that do not end when the sun sets or the body stops moving. This matters because the human organism did not evolve to distinguish neatly between physical pressure and continuous abstract demand. The same body that once stayed ready for changing land now stays ready for changing signals. Technology has also altered how effort is distributed across time. Many animals and many earlier human routines contained more obvious alternation between action and recovery. Modern life often produces a flatter pattern, where effort is less intense in any one moment but more constant across the whole day. Constant low-level expenditure can feel strangely exhausting because it offers too little contrast. The body remains partially activated, posture remains constrained, the eyes and mind remain fixed on tasks, and the older systems of vigilance keep spending energy on interpretation. This can make rest feel incomplete, even when conditions appear comfortable. Comfort, after all, is not the same thing as recovery. A chair may reduce physical strain while leaving the brain under steady load. Artificial light may extend the usable day while softening the cues that once helped regulate energy. Communication technology may reduce distance while increasing the social field the body feels responsible for tracking. None of this means technology is simply harmful, nor does it mean early human life was better in any simple sense. It means only that tools do not erase biological cost. They rearrange it. Many animals still live within environments where energy use remains closely tied to immediate physical conditions. Humans increasingly live inside environments of symbol, schedule, expectation, and mediated attention. That kind of life can be metabolically expensive in a quieter way. When human energy seems to run out quickly in the modern world, the answer is not that the body has become weak in comfort. It is that an already costly organism is now spending more of its budget on forms of effort that are harder to see, harder to interrupt, and harder to complete. The machine may take weight from the hands, but it does not necessarily take weight from the nervous system, And that may be one reason modern human fatigue can feel so deep even when the body has scarcely moved at all. The contrast between modern life and the environments in which the human body evolved becomes especially clear when we look at how recovery is supposed to work. In many animals, recovery is built directly into daily cycles. Periods of activity are followed by clear phases of rest, and the body's internal systems align with external cues such as darkness, temperature change, or seasonal rhythm. This alignment allows energy to be restored in predictable ways. In human life, however, the conditions that once supported natural recovery have shifted. Artificial lighting extends the day far beyond natural limits. Social and cognitive demands continue into hours once defined by rest, and the separation between work, vigilance, and recovery has become less distinct. The body still relies on biological systems that expect clear contrasts between exertion and rest, yet the environment often no longer provides those contrasts in the same way. This mismatch does not simply reduce comfort, it changes how energy is used and restored. When the body cannot clearly distinguish between active periods and recovery periods, energy reserves may not be replenished as effectively. Sleep patterns, hormone cycles, and metabolic regulation can become less synchronized, contributing to persistent fatigue. Animals that live closer to natural environmental rhythms often retain clearer boundaries between activity and rest. Their energy systems benefit from regularity in light exposure, movement patterns, and feeding cycles. Humans, by contrast, often live in conditions that blur these boundaries, making recovery less complete even when total time spent resting seems sufficient. Another factor lies in the nature of modern attention. Cognitive demands today are often sustained across long stretches of time without natural interruption. Tasks may require continuous focus, decision-making, and emotional regulation, even in physically inactive states. This sustained engagement keeps the nervous system in a state of partial activation, drawing on energy reserves without providing the kind of release that physical exertion followed by rest can bring. As a result, the body may experience ongoing low-level depletion rather than distinct cycles of expenditure and recovery. Over long periods, this pattern can accumulate into a persistent sense of fatigue that feels disproportionate to visible effort. It is important to recognize that this pattern is not simply a product of individual habits, but reflects a broader shift in how human life is structured. The human body evolved within environments where movement, social interaction, and rest were interwoven with natural cycles. Modern environments often separate these elements or extend them beyond their traditional boundaries. This separation can make it harder for the body to regulate energy effectively, leading to the impression that energy runs out more quickly. When comparing humans to animals, it is therefore not only differences in physical capacity or metabolism that matter, but differences in how daily life supports or disrupts natural rhythms of energy use and recovery. Animals that maintain close alignment with environmental cycles often experience more consistent energy patterns, while humans may face ongoing demands that prevent full restoration. Understanding this helps explain why human energy can feel depleted even in contexts that appear comfortable or undemanding. The issue is not simply the amount of effort exerted, but the structure of effort and rest over time. The human body remains shaped by evolutionary patterns that assumed certain rhythms, and when those rhythms are disrupted, energy balance becomes harder to maintain. This perspective offers a way to understand modern fatigue not as a failure of the body, but as a reflection of how ancient systems respond to new conditions, highlighting the complex relationship between environment, behavior, and energy that continues to shape human experience. Rest may seem like the simple answer to human exhaustion, yet rest itself reveals one of the strangest differences between humans and many animals. If human energy runs out so quickly compared to animals, the problem is not only that humans spend energy in many ways, but that human recovery is limited by the same evolutionary design that made our species adaptable. Many animals appear to recover with a completeness that humans often do not feel. A resting animal can sometimes seem fully given over to stillness, as if the body has entered a narrower and more economical state. Human rest is often less complete. Even in quiet, the body continues to regulate temperature, maintain posture, process social memory, and support a brain that rarely becomes truly cheap to run. Sleep helps, of course, and without it the human body begins to fail in visible ways. Yet sleep is not a magical reset that erases every cost. It is one part of a recovery system shaped by older environments in which human beings needed to remain somewhat responsive even while resting. From early in human history, rest was rarely absolute. A person resting near others still lived inside a social field of sound, movement, and shared vulnerability. A group sleeping in an uncertain landscape could never surrender as completely as a burrowing animal in a stable niche or a species whose defensive adaptations reduced the need for constant interpretation. Human rest was tied to light, fire, weather, group safety, childcare, and memory of danger. This does not mean early humans never slept deeply or never recovered well. It means only that recovery in our lineage was woven into a more complex world. The body had to restore itself while remaining part of a flexible social and environmental system. That old condition matters because it suggests that the human organism was never designed for perfect ease between periods of effort. Recovery had to coexist with awareness. The modern feeling of waking without fullness of energy may therefore have roots deeper than one bad night. Human beings inherited a body whose repair systems work under constraint. Muscles can recover, glycogen can be restored, tissues can heal, but these processes compete with many other claims on the same limited energy budget. The immune system may need resources. The brain continues its own demanding work during sleep. Hormonal rhythms must be maintained. Temperature must stay within workable bounds. In many animals, especially those more narrowly fitted to their ecological role, recovery may be supported by clearer cycles of exertion and rest, or by physiological strategies that allow deeper metabolic slowing. Humans seem to have followed another path. Our species invested in continuity of function. Even in rest, the organism keeps more systems partially active. This was likely useful in the long human past, where flexibility, group coordination, and environmental uncertainty made full disengagement costly. But usefulness does not remove the price. It means the price was tolerated because the larger strategy worked. The farther back we look toward the beginnings of human life, the less likely it seems that rest was ever meant to feel like total biological silence. It was restoration under watchfulness, recovery inside relationship, sleep inside an unfinished world. This also helps explain why human fatigue is not always cured in proportion to the time spent resting. Rest is not merely the absence of movement. It is a biological negotiation over how much repair can be completed while other demands remain in place. Animals that seem more durable may not always be stronger in an absolute sense. They may simply be better able to enter states in which expenditure drops more decisively and recovery becomes cleaner. Humans, by contrast, carry a body whose strengths depend on remaining partly available to thought, memory, social connection, and changing conditions. So when human energy seems brief beside animal energy, part of the answer may lie here as well. We are not only a species that spends heavily, we are also a species that cannot always recover with perfect simplicity, because the same evolutionary path that made us flexible, social, and mentally awake also placed limits on how completely we can ever power down and begin again. Recovery in humans is not only limited by how long the body rests, but by how deeply it can reduce internal activity while still preserving essential functions. In many animals, recovery involves entering physiological states in which energy expenditure drops sharply. Some species lower their body temperature, slow their heart rate, or reduce neural activity to conserve energy over long stretches of time. These mechanisms allow the body to replenish reserves more efficiently and can support long periods without food or movement. Humans, however, rarely enter such extreme states. Even during sleep, core temperature remains relatively stable. The brain continues to cycle through complex patterns of activity, and the body maintains systems that support cognition, memory, and social functioning. This means that recovery in humans is often partial rather than complete. The difference is not simply a matter of rest quality, but of evolutionary design. Human ancestors evolved in environments where remaining responsive to surroundings was often more advantageous than fully disengaging. Vulnerability during deep inactivity could carry significant risks, particularly for a species that lacked the natural armor, speed, or camouflage found in many other animals. As a result, human biology appears to favor lighter forms of shutdown, maintaining a level of readiness even during rest. This pattern supports survival but also limits the depth of energy restoration, Another aspect of recovery relates to the demands placed on internal regulation. The human body must maintain a stable internal environment across a wide range of external conditions. Temperature regulation, hydration balance, immune activity, and tissue repair all continue during rest, drawing on energy reserves. In animals whose environments remain more consistent or whose bodies are more specialized, some of these regulatory demands may be lower or more narrowly tuned. Humans, by contrast, often face a broader range of internal adjustments, even in relatively stable settings. This contributes to a baseline level of energy use that persists throughout the day and night. The structure of human sleep also reflects these constraints. Sleep is divided into multiple stages, each associated with different forms of neural activity and bodily maintenance. While these stages support essential processes such as memory consolidation and cellular repair, they do not represent a complete suspension of activity. The brain remains engaged, processing information and maintaining networks that support future behavior. This ongoing activity helps explain why sleep, though vital, does not always eliminate fatigue entirely. In early human contexts, this balance between rest and readiness may have offered clear advantages. Remaining somewhat alert could help individuals respond to threats, care for dependents, or adapt to sudden changes. However, this same pattern means that energy recovery is inherently limited. In modern life, where cognitive and social demands can extend late into the day, the ability to reach deep and sustained recovery may be further constrained. The result is a sense of ongoing fatigue that does not always correspond to the amount of rest obtained. When comparing humans to animals, it is therefore important to recognize that recovery strategies differ as much as activity patterns. Many animals can enter states of deeper energy conservation, reducing metabolic activity more dramatically and allowing more complete restoration. Humans, by contrast, maintain a higher baseline of physiological and neural activity even during rest. This does not mean that human recovery is defective, but that it operates within a different set of constraints shaped by evolutionary pressures. Understanding this distinction helps clarify why energy in humans can feel fragile, and why rest does not always bring the level of renewal that might be expected. The limits of human recovery become clearest when we remember that rest is not a separate world from the rest of life, but a continuation of the same biological compromises that shape waking energy. The human body does not move from effort into pure restoration as if crossing a clean border. It carries much of itself across that border. Muscles may soften, the eyes may close, and outward action may stop, yet the deeper organism continues its work. Tissue repair proceeds, immune surveillance continues, temperature must still be managed, and the brain remains active in patterns that help preserve memory, regulate internal timing, and prepare the body for the next day. In this sense, human recovery is not a full shutdown, followed by a full restart. It is a partial lowering of demand inside a system that keeps many responsibilities alive at once. This may be one reason human energy can feel as though it never fully returns with perfect completeness. Many animals seem to enter recovery more decisively. Their bodies may settle into simpler cycles in which exertion and restoration are more sharply separated, or they may rely on physiological strategies that reduce activity more deeply when conditions allow. Humans appear to recover within narrower margins. That pattern likely has old roots. In early human settings, full disengagement may have carried risk. A sleeping person still remained part of a group, part of a landscape, part of an environment where sound, cold, movement, and social responsibility could matter at any hour. The body that survived under such conditions may not have been the body best at disappearing completely into rest. It may have been the body best at restoring enough while remaining somewhat available to change. That is a very different kind of recovery. It is recovery under tension, even if the tension is subtle. The farther back we look toward the beginnings of human life, the more rest seems woven into uncertainty rather than protected from it. A body that must remain able to respond cannot always invest all available energy into repair. Some portion must remain held in reserve for regulation, awareness, and readiness. That held reserve has a cost. It means restoration may be slower, less absolute, and more easily disturbed than in animals whose ecological role allows deeper metabolic quiet. The human story of fatigue therefore includes not only high expenditure but limited recovery depth. This becomes even more important when we remember that human rest is shaped by social life as well as biology. Sleep and restoration in our lineage were rarely only solitary physiological events. They occurred in relation to infants, partners, elders, weather, fire, shared safety, and remembered danger. The body did not only need to heal, it needed to remain part of a living network. That social embeddedness may have protected survival, but it also meant recovery was never purely private. In modern life, this ancient pattern often continues in disguised form. The body may lie still, yet mental and emotional systems remain partly engaged, carrying unresolved signals, unfinished thought, and the broader burden of social existence. Even without turning too quickly to modern explanations, the deeper point remains. Human beings belong to a species whose recovery system was shaped by the same evolutionary logic that shaped its costly brain, adaptable body, and cooperative way of life. Rest supports us, but it does not erase the structure of what we are. So when human energy seems to run out quickly compared to animals, the answer is not only that we spend too much, it is also that we recover within a design that rarely allows complete surrender. We heal, but under conditions. We restore, but partially. We sleep, but as organisms still carrying memory, vigilance, regulation, and relationship through the night, and that quiet incompleteness may be one of the oldest reasons human energy so often feels easier to lose than to fully regain. The feeling that human energy drains too quickly becomes especially sharp when viewed through the lens of mismatch, the gap between the environments that shaped human biology and the environments in which many people now live. For most of human existence, daily life required sustained physical engagement with the world. Movement was not optional but woven into survival. Searching for food, maintaining shelter, traveling across terrain, and responding to seasonal change formed a natural rhythm that distributed physical effort across the day. In that context, energy expenditure followed patterns that the body was shaped to manage. The modern world has changed this balance in ways that are subtle but profound. Physical effort is often concentrated into brief periods or removed almost entirely, while cognitive and emotional demands persist or even intensify. This shift does not eliminate energy use, it reshapes it. The human body still carries systems built for endurance, vigilance, and adaptation, but the demands placed on those systems now differ from those that shaped them. One consequence of this mismatch is that the body may remain in a state of low-level activation for extended periods. Sitting for long hours does not necessarily equate to rest, because posture must still be maintained, attention remains engaged, and social or informational demands continue. The nervous system may remain alert in response to work, communication, or uncertainty, drawing energy without providing the clear signals that once marked the end of effort. In earlier environments, physical fatigue often aligned with natural cues for rest, such as darkness, temperature shifts, or the completion of essential tasks. Today, those cues are often blurred or overridden by artificial lighting, extended schedules, and continuous access to information. This can interfere with the body's ability to transition fully into restorative states. The result is a pattern in which energy is expended continuously but recovered less completely, leading to a persistent sense of depletion. The mismatch also affects how the body interprets its own state. Systems that evolve to respond to immediate physical challenges may not respond in the same way to prolonged cognitive or emotional demands. A person may feel exhausted without having engaged in strenuous physical activity, creating a disconnect between perceived effort and felt fatigue. This disconnect can be difficult to interpret, yet it reflects the underlying reality that energy use in humans is not limited to visible exertion. When comparing humans to animals, this difference becomes clearer. Many animals continue to live within environmental rhythms that align closely with their evolutionary adaptations. Their activity and rest patterns remain tied to daylight, temperature, and resource availability. Humans, by contrast, often live in environments where these rhythms are less pronounced and where demands on attention and decision-making extend beyond traditional boundaries. This does not mean that human biology has failed, but rather that it is operating within conditions that differ significantly from those under which it evolved. The experience of running out of energy quickly can therefore be understood not only as a result of internal biology, but as an interaction between biology and environment. Recognizing this interaction helps move the question beyond simple explanations of strength or endurance. It highlights the importance of context in understanding human fatigue. The body's systems for energy use and recovery were shaped in environments that demanded continuous but varied engagement with the world. When those patterns are altered, the balance between expenditure and restoration can shift in ways that feel difficult to manage. This perspective suggests that the sensation of rapid energy loss is not simply a modern inconvenience, but part of a deeper story about how human biology responds to changing conditions. Mismatch becomes even more visible when we look at what the human body expects from an ordinary day and what many modern days actually provide. For most of human history, effort was usually embedded in the world itself. The body rose into changing light, moved across uneven ground, adjusted to temperature, carried loads, watched the sky, and linked action with immediate material outcomes. Food, shelter, safety, and social belonging were not abstract categories. They were woven into movement, waiting, and shared labor. In that setting, energy expenditure was rarely simple, but it was often legible to the body. A long walk produced physical fatigue. Cold demanded heat production. Hunger led to foraging, or preparation. Rest came, not as a separate idea, but as part of a visible cycle. Modern life often disrupts that legibility. A person may wake indoors, remain seated for much of the day, and still experience a level of depletion that feels strangely disproportionate to outward effort. This is not always because the body is weaker than before. It is often because the older signals that once organized expenditure have been replaced by demands that are harder for the body to resolve. Attention must be sustained without much movement. Decisions arrive continuously without clear completion. Social evaluation continues across work, messages, schedules, and unspoken expectations. The nervous system remains active, but the activity is diffuse rather than grounded. In evolutionary terms, this matters because human biology was shaped not only for effort, but for effort that had rhythm, location, and consequence. The body could calibrate itself against changing terrain, changing light, and changing task. In modern settings, the task may change constantly while the body remains in the same chair, under the same light, with the same posture. This creates a strange condition in which multiple systems are engaged, but few are allowed to complete a full cycle of effort and release. The muscles hold low-level tension, the eyes remain fixed, the brain tracks abstract problems, and the social mind continues scanning for response. None of this looks dramatic from the outside, yet it spends energy steadily. The mismatch also appears in time itself. Earlier human life was certainly not easy, but many demands had clearer boundaries. The day darkened. Work paused. Distance limited social reach. Information did not continue without end. Today the human organism often lives in a flatter, more extended field of activation. Signals continue into the evening, and tasks bleed into one another without the closure that older environments may have provided more naturally. This can make recovery less effective, because the body is not only spending energy, it is spending it inside a pattern with too few natural edges. Animals that seem more stable in their energy use are often still living within narrower loops between action and pause, demand and recovery. Humans increasingly live in loops that remain open. That openness may be useful for productivity, coordination, and long-range planning, but it is metabolically expensive. It asks the body to maintain readiness without the grounding effect of older physical rhythms. The result is not simply tiredness after work. It is a more confusing form of depletion in which energy feels used up by things the body cannot easily name. This helps explain why the human experience of fatigue in modern life is so often accompanied by a sense of vagueness, as though something has been spent without anything tangible being built or carried. From the deeper perspective of human origins, that feeling makes sense. The body we inherited was shaped for a world in which effort usually meant direct engagement with place, season, and task. When that same body must spend its energy inside abstraction, interruption, and prolonged low-level activation, the old balance begins to loosen, and human energy can seem to run out, not because life contains too much movement, but because it contains too little of the kind of movement and rhythm that once made expenditure easier to understand and easier to recover from. The mismatch between human biology and modern life becomes most revealing when we stop thinking of fatigue as a private weakness and begins seeing it as a signal from a body living in conditions it was not narrowly shaped for. Human beings did not evolve in a world of constant indoor light, prolonged sitting, continuous symbolic work, and endless low-level social contact extending beyond physical presence. For most of the human story, daily life placed the body inside a landscape that gave effort a more tangible structure. Movement was tied to finding, carrying, building, preparing, watching, and returning. Rest was tied more closely to darkness, weather, safety, and the temporary completion of necessary tasks. This did not make early human life easy, and it does not mean our ancestors moved through the world in perfect balance, but it does suggest that the body was spending energy in ways that were easier for its systems to register and resolve. Modern life often breaks that pattern. The body may no longer walk far, lift much, or work against cold and terrain in the same old way, yet it remains under demand for long hours. The demand has shifted into attention, posture, planning, emotional restraint, rapid decision-making, and continual response to signals that rarely end cleanly. This creates a strange biological situation. Energy is being spent, but the body may not receive the older forms of feedback that once matched expenditure to recovery. A person may feel tired without feeling that anything concrete has been completed. That confusion is part of the mismatch itself. The human organism was shaped across a long history in which effort was usually linked to place and consequence. You walked and arrived somewhere. You gathered and held food in your hands. You worked with others and saw a shelter, a fire, a path, or a tool take shape. Even social strain and uncertainty were embedded in a visible environment. Today, much expenditure unfolds in abstraction. The eyes remain fixed on symbols, the spine holds the same position, the hands repeat small controlled actions, and the mind carries responsibilities that extend across hours without a natural stopping point. The body is still paying, but the payment is harder to interpret. This can make fatigue feel heavier and more mysterious than simple physical tiredness. It also helps explain why modern exhaustion often lingers. Systems shaped for cycles of exertion and release now experience long stretches of partial activation. Muscles may not be fully used, yet they are not fully at rest. The brain may not be facing a direct physical threat, yet it remains engaged in monitoring, comparing, anticipating, and regulating. Social awareness continues through messages, roles, expectations, and invisible obligations. In this setting, recovery becomes harder not only because the body spends energy, but because the body struggles to locate the edges of effort. Animals that seem more stable in their energy often remain more tightly linked to recurring environmental cues. Their expenditure and rest may still fit older ecological loops. Humans increasingly live in loops made of schedule, symbol, and unfinished attention. That kind of life can make the body feel as though it is always spending slightly more than it can comfortably replace. The deeper human story, therefore, does not end with the claim that modern life is bad or that the past was better. The more careful point is that the human body was shaped for one pattern of demand and now often lives inside another. That difference matters. It helps explain why human energy can seem to run out quickly, even when life appears physically easier than before. We are carrying an ancient organism into environments that ask for sustained readiness without enough natural closure, thought without enough embodied release, and social engagement without enough true quiet. When seen this way, fatigue becomes less like a personal failure and more like a historical trace still moving through the body, a reminder that human energy was never only about strength, but about fit, rhythm, and the difficult work of living inside a world that changes faster than the body that must endure it. By the time we reach this point, the question has changed in a quiet but important way. At first it may have sounded like a comparison of strength, as if humans simply fail where animals succeed, as if our energy runs out quickly because something in us is poorly made. But the longer view suggests a different picture. Human energy is not weak in any simple sense. It is expensive. It is expensive because the human body is carrying too many jobs at once, many of them ancient, many of them invisible, and many of them tied to advantages that helped our species endure. We stand upright and pay for balance. We move with flexible hands and pay for coordination. We carry a large, active brain and pay for thought even in silence. We live socially and pay for attention to other minds. We adapt broadly and pay for regulation across changing conditions. We rest, but not with the full simplicity of creatures whose bodies can narrow their needs more completely. When compared to many animals, the human body often appears less economical because it was not shaped around narrow economy alone. It was shaped around breadth. That breadth allowed survival across mixed landscapes, shifting climates, uncertain food, and complex group life. It allowed humans to remember, plan, teach, cooperate, and adjust. Yet every one of those strengths widened the energy burden. The body that could do more also had to spend more merely to remain ready. This is why human fatigue can be so confusing. The body may feel emptied even when no obvious physical labor has taken place, because the expenditure is spread across posture, temperature control, memory, social vigilance, emotional regulation, anticipation, and the quiet maintenance of an organism that rarely goes fully still inside itself. In animals, we often admire what looks like steady endurance, but that steadiness may come from specialization, clear ecological fit, or deeper forms of conservation. Humans chose, through evolution rather than intention, a different bargain. We became costly in exchange for flexibility. That bargain succeeded so well that our species spread almost everywhere. But success does not mean cheapness. It means the cost was survivable. The modern world has made this old pattern easier to notice. Many visible physical burdens have been reduced, yet the human organism continues to spend energy according to a deeper biological history. In some ways, it now spends that energy inside even stranger conditions, where attention remains active, social demands remain extended, and recovery is often incomplete. Still, the deeper truth is older than modern life. Human beings have long carried a form of energy that is divided before the day begins. It is divided between body and brain, between self and group, between present need and future preparation. When seen from this long perspective, quick exhaustion stops looking like a personal defect. It begins to look like the natural shadow of a species that survived by staying broadly responsive rather than narrowly efficient. This does not solve the problem of fatigue, and it does not mean every tired feeling is wise or meaningful, but it does offer a gentler interpretation of the body. The human body may not be the most economical body in nature, yet it is one of the most burdened with overlapping forms of life. It must move, think, remember, regulate, and belong, all while adapting to worlds that keep changing faster than flesh can fully redesign itself. So the question is no longer only why human energy runs out so quickly compared to animals. The quieter question is whether what we call exhaustion is sometimes the visible edge of a much older truth, that to be human has always meant living inside a body whose strengths and costs are inseparable, and whose energy was never meant to feel simple. If human energy has seemed fragile all along this journey, the final step is to see that fragility and value can belong to the same body. Nature does not reward every species with the same kind of efficiency, because survival is never solved in only one way. Some animals endure by narrowing their needs, refining one movement, one habitat, one feeding pattern, or one cycle of rest and action until the body fits the world with remarkable economy. Humans endured by doing something riskier. We became a species that carried more unfinished work inside the body itself. We carried movement without perfect mechanical ease, intelligence without cheap fuel use, social life without emotional simplicity, and adaptability without the metabolic calm of a narrow ecological role. This helps explain why the human organism can feel as though it is always paying in advance. Before the muscles tire, other systems have already drawn from the same limited reserve. The brain has been active, the posture has been maintained, the social mind has been alert, the inner organs have been regulating, and the body has been trying to remain prepared for change. The result is that human energy often feels less like a full tank waiting to be used, and more like a shared inheritance constantly divided among many claimants. That division is not a mistake added late in history. It is part of the structure of being human. From the deep beginning of our species, survival depended on overlapping capacities rather than singular perfection. A person had to notice the landscape, remember the path, read the group, endure the weather, manage the body, and prepare for what had not yet happened. This broad field of responsibility did not always produce comfort, but it produced continuity. It allowed human beings to remain present in places and situations where a more specialized creature might have failed. In that sense, our quick exhaustion may be related not only to burden but to range. We do not merely spend energy to exist in one niche, we spend energy to remain possible across many conditions at once. This broader perspective does not deny the reality of fatigue, it deepens it. The body is not betraying us when it grows tired. It may be revealing how much it is carrying beneath ordinary life. A person may think they have done very little, yet the organism may have been working across multiple layers all day, balancing thought, restraint, interpretation, memory, and low-level vigilance while also supporting the ordinary maintenance of flesh. Compared with many animals, that is an expensive way to live. But expense is not the same as failure. It may be the price of becoming a creature that can transform landscapes, preserve knowledge, care across generations, and imagine futures beyond immediate instinct. Even modern fatigue, strange and often discouraging as it feels, may still carry the outline of this older inheritance. The body is still operating with the same ancient logic, even when the world around it has changed. It still spends energy on readiness, belonging, anticipation, and repair, even when the setting no longer resembles the one that shaped those habits. This is why the final understanding is gentler than the opening question. Human beings do not run out of energy quickly because they are simply worse at life than animals. They run out of energy quickly because the human form was built around costly strengths whose benefits and burdens cannot be separated. We are a species of divided expenditure, of partial rest, of broad adaptation, of intelligence that never comes free. To recognize this is not to romanticize exhaustion, and it is not to turn tiredness into a virtue. It is only to see more clearly that the human body is not a failed animal. It is a layered animal. Its energy disappears into many invisible places because human life has always unfolded across many invisible demands. And perhaps the quiet lesson inside that long history is that the body deserves to be understood not as a machine that should never feel tired, but as a living record of everything our species had to become in order to remain here, still thinking, still adapting, and still asking what this strange cost of being human has always meant. The final step in understanding why human energy seems to disappear so quickly is not to search for a single missing element, but to see the pattern as a whole. Across the long arc of human existence, the body has never been optimized for narrow efficiency. It has been shaped to carry multiple forms of readiness at the same time. From the earliest periods of human life, the organism that became us did not survive by being the fastest, the strongest, or the most economical. It survived by being able to remain responsive across many changing demands. That meant a body that could travel long distances when needed, but also stop and think. A body that could use tools, but also use memory. A body that could coordinate with others, manage emotion, regulate temperature, recover from strain, and adapt to new environments. Each of these capacities added to survival, yet each also added to cost. The result was not a simple energy system, but a layered one. In this system, the body rarely reaches a point where expenditure truly falls to zero. Even in rest, repair continues, awareness lingers, and regulation persists. This constant background activity helps explain why fatigue can appear even without dramatic effort. It is not always a sign of failure or weakness, but often a signal that many systems are running at once. When humans compare themselves to animals, the comparison can feel discouraging. Many animals appear to conserve energy more cleanly, resting deeply, moving efficiently, and seeming less prone to depletion. Yet this difference does not necessarily reflect a superiority in one direction. It reflects different evolutionary strategies. Animals that appear more efficient often do so by fitting tightly into specific ecological roles. Their lives, while not easy, may demand fewer simultaneous forms of adaptation. Humans evolved along a path that prioritized breadth over narrow optimization. That breadth allowed human beings to endure in environments that varied widely in climate, resources, and social structure. It supported learning across generations, cooperation in complex groups, and survival in places where specialization alone might have failed. But the cost of that breadth is written into the human experience of energy. It is written into the way the body allocates resources across movement, cognition, social connection, and internal maintenance. It is written into the way recovery remains partial and vigilance never fully disappears. This perspective invites a different way of thinking about fatigue. Rather than viewing exhaustion as simply a personal shortcoming or a modern problem, it can be understood as part of a deeper biological story. The human body carries an ancient pattern in which energy is widely distributed, constantly managed, and rarely conserved in simple ways. Modern life does not erase this pattern. In many cases, it amplifies it by layering new cognitive and social demands onto an already complex system. Recognizing this does not solve fatigue on its own, but it reframes it. It suggests that the human experience of running out of energy quickly is not an isolated flaw, but a consequence of being a species built for adaptability, learning, and shared life. The question then becomes less about why humans fall short, and more about how to understand the cost of the very traits that allowed human beings to persist across deep time. In that light, fatigue is not only a limit, it is also a trace of the same capacities that shaped human survival. And perhaps the most enduring question is not simply why human energy runs out so quickly compared to animals, but what it means to live as a creature whose greatest strengths and greatest costs are bound together in the same body. To close this journey, it helps to hold the question gently rather than trying to force a single sharp answer. Human energy does not run out quickly because the human body is broken, nor because other animals are simply better at life. The story is slower and older than that. Across the long history of our species, the human body became something layered rather than simple. It learned to move through different terrains without being perfectly built for any one of them. It learned to live on many foods rather than one ideal source. It learned to carry memory, language, and social bonds, not as optional additions, but as essential parts of survival. Each of these strengths helped human beings endure when the world shifted, but each of them also drew from the same finite pool of energy. Over time, the human organism became a place where many demands meet at once. The need to move, to think, to belong, to regulate, to anticipate, and to recover. Because of this, energy in humans has never been a simple resource that fills and empties cleanly. It has always been divided across many systems, some visible and some hidden. When compared to animals whose lives fit more narrowly into stable ecological patterns, humans often appear less economical, more easily tired, and less capable of deep, uncomplicated recovery. Yet that comparison can be misleading if it is read only as weakness. Many animals conserve energy by narrowing their lives around specific conditions. Humans survived by widening their lives across many conditions. That difference shaped everything that followed. In the modern world, this old pattern has not disappeared. Instead, it often becomes more visible. Physical demands may lessen while mental and social demands expand. Rhythms that once balanced exertion and rest can become blurred. Recovery can feel incomplete even when time for rest is available. In this context, fatigue is not only a response to what happens in a single day, it is a response to the deeper structure of a body that was built to remain ready across uncertainty. This perspective does not eliminate tiredness, but it changes its meaning. Exhaustion becomes less like a personal failure and more like an echo of an evolutionary strategy that valued flexibility, awareness, and cooperation over narrow efficiency. Seen in this light, the human body is not simply a fragile machine that runs down too quickly. It is a complex system carrying the legacy of long adaptation, one that spends energy widely because it was built to meet many kinds of challenges. Recognizing this does not provide an easy solution, but it does invite a different kind of understanding. It suggests that the feeling of running out of energy may not always be a sign that something has gone wrong, but a reminder of how much the human organism is quietly sustaining beneath the surface. And perhaps the question that remains, even now, is not only why human energy runs out so quickly compared to animals, but what it truly means to live as a being whose greatest strengths and greatest costs are woven together so closely that one can never be fully separated from the other.